Kendra has just shown up, so let me let her in. Uh, okay. I think someone's microphone is on that you may not realize it is. Okay. All right, got Kendra here, so that gets us up to 8 students, which is good. Hopefully more will be coming in. I think I need to minimize this. I've already done. Okay. Oh, here's Denisha. Good deal. Let me get her in. I need a bigger desk to teach from here. Denisha is here. Okay. All right. So that gets us up to 9 students. 3, 6, 9. Got it. Okay. The first question we had was on the moon, and I usually am out around 10ish, and the last couple of nights it's been very dark, which indicates to me there's not much moon there if there is, or because of cloud cover, which either could have been the case. But if it was very low in the sky, like I was explaining, we're surrounded by trees here, so if it's low in the sky, I wouldn't see it then. It has to be pretty high in the sky for me to see it from our backyard. So it may be that that there is, and whoever was asking me, I can't remember who it was now, was saying it was a very thin crescent. So either it's right at the end of a cycle or right at the beginning of the next cycle. So going either just about to become a new moon or just came off a new moon. And I just let Jackson in. So we're now up to 10 students. Broke the double digits here. 3, 6, 9, 10. Got it. Okay. Good to see people keep coming in. And if any of you were having trouble getting in, it's because my internet went out and I wasn't able to get in to let you in. But I had to change internet providers, and then that enabled me to get in. So sorry about the delay there. All right. Now, that was on the moon. Were there any other issues or questions that did come up? Seemed like someone was getting ready to say something when someone else came in the classroom, in from the writing room. Okay, so let's go over where we are and where we're heading. We're in great shape in this course, at least it feels like it to me. Today we're going to start on chapter 23, Weather and Climate. We're going to go for until 3:45, stop there, and at 3:45 we're going to do the lab from chapter 20. We skipped chapters 21 and 21 and 22, and we'll be picking up, going back and do the lab from chapter 20. Now there's nothing special about 20 in it, it's just the lab that wound up pairing up with that, and it's on topographic maps, which is something we sort of talked about in an earlier time. And you know, topographic maps do involve shaping their surface, so yeah, it does sort of have a connection, but probably isn't as strong a connection as say the 3 astronomy chapters were. These that have been since astronomy have not been as focused. Now the next 2 labs, weather and climate, is going to deal with weather, and the oceanography or waters, earth waters, that will definitely deal with that. So those will be very, very focused again. So we'll get started in 23 today, and this I was noticing of most of the, let me see, I'll bring it back up. I don't think you can see it. Whoops, that's the wrong one. Okay, so let me bring this back up. Here we go. Of all the chapters we've done, that would be 14 through where we are now. This is just the size of the chapters. 14 was 2.2 KB, kilobytes. 15 was 3.6. 16 was 3.0, 17 3.6, 18 2.5, 19 3.7, 20 2.8, 21 2.9, 22, well, we didn't do 21 and 22, 3.8. Chapter 23, 9,430. That's 9.4. This is close to being 3 times the size, between 2 and 3 times the size of any chapter. Now this is just the PowerPoints, so there's going to be sort of a long chapter. Okay, chapter 24 is back down in the 2.6 range, so this is going to be a fairly long chapter. I doubt if we'll get much more than half of it done today, so hopefully we'll be able to finish it up on Thursday. Okay, so what we're going to do today is chapter 23 up until 3:45. Then we'll stop and do the lab and I did post the lab out there, and you'll see the lab on its 2 parts, and both parts, one's a PDF file and one is a doc file, and the doc file has within it a HTML code, URL code that you will have to access from there. So I don't know how restricted y'all are on your capabilities. I'm pretty restrictive. I don't know how to handle this too well, but I know if some of you are operating mostly from a cell phone, it may be tough to follow, but we'll try to go over everything in detail so you can get it all down. And it's being recorded, so you'll have the recording that you can fall back on. And it was recorded last summer, so if you wanted to get started on before this recording gets out there, it will be there as well. Same lab. Okay, so then hopefully on Thursday we'll finish chapter 23. And even if we don't finish 23 completely, because it is a very long chapter, if we don't finish 23, we can still finish it on Tuesday of next week and have plenty of time to do the lab on 23 Tuesday afternoon. And then whenever we finish 23, we'll start 24, not this week, but next week sometime, and then we'll do on 24 as long or short as it takes. And then the following week on Tuesday we'll do the finish up 24. If we haven't finished it by then, we will do the lab for 24. I'll give you the test for 24, and then of course will be the final exam, which is probably going to be the easiest test you've had all term in this course anyway, because it's matching, not multiple choice, not fill in the blanks, but matching. So it's a pretty simple, easy, straightforward test. And that will wrap us up for next week. Now I have one more question for you. Have any of you seen anything about student course evaluations for the first mini-term courses? Has anyone seen an email or message or anything about that? I haven't either, but like I say, I'm probably a day and a half or 2 days behind on emails right now. I got caught up over the weekend, but I've fallen behind yesterday and today. So anyway, I haven't seen it either. Watch out for that, because they're going to open them up. Last time they did it in the summer, I mean like the day before the class was to be over with. So watch out for those. Please do the student course evaluations when they open. Now I can't tell you how they're going to do those, because this is our first term on Banner, and I don't know if that impacts the student course evaluations or not. I wouldn't think it should, but it may. So if that's the case, watch for them. Whoa, that's not what I wanted to do. I wanted to minimize, not okay. So all that being said, let me go on and get the screencast-o-matic. I can't talk. The PowerPoint started. Oh, here comes Labrina. Let me get her in. Okay. All right, there's Labrina. So that gets us up to 2, 4, 6, 8, 10, 11 students. Is that right? Wait, here we go. Whoa, we've lost somebody, I think. So hopefully they'll be coming back in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Yeah. Somebody bowed out. See, this is the opposite of Hotel California, if any of you remember that very old song. It read, the way the words went on that, you can check out anytime you want, but you can never leave. Well, here you can check out anytime you want, and I'll never know that you left, so it's not quite the same thing. So anyway, we are in this. Let me get the slideshow started. Can everyone see my slide now? Anyone who's looking? Yay or nay? Okay. So here we have chapter 23, weather and climate. That is a pretty impressive picture of a major storm coming in. I guess it's coming in and not going out. The water looks awfully calm, and I can't figure out why in the world a sailboat would be out there, or even that other boat out there, approaching that kind of weather system. I would be making it to shore if I were in their boats, okay? But there's weather at work, okay? We'll be talking about some of that coming up. Here's the core concept for the chapter, and this is on your page 573 if you have the big book. I assume it's 23-1 if you have the small book. Solar energy, slide reads a little differently. In the slide set it says solar radiation. In the textbook it says solar energy drives the cycles in the Earth's atmosphere, and that's true for most of the case. We'll talk about a little bit where it doesn't. And some of those cycles determine weather and climate. And that's sort of a nebulous and sort of broad-brushed approach there, but that's what we're going to be talking about. Now, if I could get that box out of the way, I'd move it, but I can't. I don't know if Zoom does it, PowerPoint does, I don't know who does it, but there it just faded out. You can see here, this is the Gulf of Mexico. There's Florida. We are getting behind the block now, but here's the boundary of the Gulf of Mexico over here, and I wish that box would be out of the way. Can't get it to move though. It does fade out after a while, but it looks like most of the cloud cover is down here over the Gulf. Hardly any cloud cover until you get well up here and here over the land. Okay, there was my brief window and it disappeared. Okay, I'm almost certain, if my geography is right, that this is probably the Mississippi River right here. It's sure what it looks like, but I may be wrong on that. I wish the block was out of the way. But anyway, that's a satellite shot. I'm pretty sure it could be a very, very high flying aircraft. But I'm pretty sure this is Louisiana sticking out here. And as we talked about in the last chapter, a lot of Louisiana, if that would ever move out of the way, my guess is delta. It's land that's washed from way up north, way west and east and all over the place. The silt, the sand, the clays have washed down and deposited out the mouth of the Mississippi River, and so that's why Louisiana sticks out into the Gulf like that. That's just about totally delta area. Okay, we talked about that in the last chapter. What we're talking about now is weather and climate, which is different. And you notice here on the east side in the Atlantic, again, the clouds are over the water, not so much over the land, though there is some low cloud cover here. But this is weather, okay? And the moisture comes from the sea, okay? So that's typical of where the clouds will be hanging out. So that's our basic thing. Solar energy, which radiation is a form of solar energy, drives cycles in the Earth's atmosphere. Some of those cycles determine the weather and climate. Okay, so the first subsection here, 23.1, clouds and precipitation. Okay, and we'll talk about each of those words to varying degrees. Probably we'll spend more time on precipitation, but we're going to spend quite a bit of time on clouds too. Now, if you have the big books, it probably will help you understand things better if you either read through or at least scroll through the previous chapter, chapter 22, which is on the atmosphere. Traditionally, when we're in class, things don't move quite as rapidly as they do virtually, so I had always had to leave out that chapter because I wanted to get to 23 and 24. Now that we don't have field trips and things like this, I have more time, but the books are set up the way it used to be. So sorry about that. Sorry you missed the field trips, and sorry that I didn't have provision for chapter 22. That would have been interesting. So let's look at hey, if you notice anything about this book, just about everything is given in cycles. Everything goes around, comes around. You've heard that phrase before. Well, weather, climate, rock cycle, all sorts of cycles. Now we're talking about the hydrologic cycle. When you see hydro, most of the time that implies water. So this is the water cycle, hydrologic cycle. Where does it begin? In some sense, though it's a cycle, so where does a wheel begin? It's hard to say. But let's start with evaporating off the ocean. And again, this box is right in the way, but you see the ocean's down here. Like I said, that's where the clouds come from. Your sun, the solar energy, solar radiation is what's evaporating the water from the oceans, and it goes upward because it's adding energy to it. It's moving upward. Okay, now once it gets far enough up there, it begins to cool off, and when it cools off, then it forms clouds. The water vapor here is not visible, okay, most of the time. It's basically evaporated into the air, but when it cools off enough, it forms little droplets, and that's what we see as clouds. Then the wind cycle, and that's caused by a couple of different things, usually ultimately drives that across land. Once it gets over land, especially if it hits a mountain range or something like that, it cools off even more, so that then precipitation happens. The moisture comes out of the clouds. It hits the ground, like we said before, and when it hits the ground, most of it ultimately heads back to the ocean. That's the completing the cycle. Everything goes around. Okay. Now, there's a lot of shortcuts here, and we'll talk about that in a minute. So it's transported, it evaporates from the ocean into the atmosphere. The atmosphere, it typically forms as clouds. Once it forms as cloud, then it's transported through the atmosphere, predominantly by winds, and then at some point condenses and precipitates. Now, evaporation is going from liquid to gas phase or state, whichever you want to call it. Condensation is when it goes from a gaseous state or phase to a liquid state again. That's condensing. If you've ever noticed before, and I'm pretty sure you have since you live in the Southeast, if you have a glass of ice water or iced tea, you set it out on the table, it's almost no time before there's water droplets all over the outside of that glass. Why? Because the glass is cooler than the air surrounding it. The air surrounding it is filled with moisture, and when the moisture cools, it condenses back to being a liquid again. It's water vapor in the air, but condenses back to being water droplets on your glass. That's what condensation is. precipitation is when those droplets fall out of the sky. Okay? Basically, precipitation means to come out, to fall. Okay? It's not just rain. Anything can precipitate. Coming out, falling. Okay? And then ultimately the water makes its way back to the oceans again. Down the Mississippi to the Gulf of Mexico, okay, as the old song goes. Okay? Now, there's many smaller subcycles can happen. For instance, this cloud could form a thunderstorm and rain right back into the ocean. So now it's a really short cycle here. It just goes up in the air and comes back down to the ocean. That's a smaller subcycle. Okay? Or it could come down on land, and then rather than going back to sea, go to a large lake or something, and then evaporate from the lake, and there's your subcycle. In fact, in western New York State, right on the Lake Erie, I believe it is, Rochester, Buffalo, New York, especially Buffalo, those areas out there, they get quite often what they call in the wintertime lake effect snow. That snow that's not come from precipitation off the ocean, it came from, evaporation off the ocean, it came from evaporation off the Great Lakes. And that's why they get some of their heavy snowfall in the winter, not from an ocean, but from a lake. That's where it evaporated from. So there could be many subcycles, okay? Actually here, it can go around the cycle for quite a while. We hope that some of this moisture goes into the ground and maybe stays there for a while, maybe a long time before it gets back to the ocean. Okay, we'll talk about that later. Now, let's first start with the clouds. How are clouds formed? This is on page 575, cloud forming processes. Okay, now here's a term, and that term is the dew point. Now, what in the world do we mean by the dew point? That is the temperature. It's a temperature point, the dew point, just like the boiling point is a temperature, the freezing point is a temperature. The dew point is a temperature. Now, most of the time, the freezing point of water is very close to 32 degrees Fahrenheit or 0 degrees Celsius. Boiling point of water is very close to 212 degrees Fahrenheit, 100 degrees Celsius. Those are sort of fixed. What a dew point is, it's where the water comes out of the gaseous phase into the liquid phase, where it condenses, becomes dew. Well, that depends on several things. Number one, how much moisture is in the air to begin with. And number two, what the ambient temperature is, because that's the dew point. That's why it's going to come out. So if it's a very dry air mass, it's going to have a very, very, very low dew point. In fact, it may be close to freezing or below freezing, and that's what creates snow rather than rain. However, with very, very humid air, like the air that came up out of the Gulf when the hurricane or tropical storm or depression came through, that was loaded with moisture, so the dew point was quite high then. So it didn't have to get very cold at night before you had a good coating of dew on your grass, on your windshield of your car, or wherever, because the dew point was quite high, because it didn't have to drop very far before the water started condensing. Okay. So, what the clouds do, they form when air masses are cooled to their dew point. And that's why I said the sun shining down on the ocean or lake or whatever it's shining on, and he's evaporating the water, and the evaporated water goes into the air, not as clouds, it goes in as a gas. Okay? You don't see it. You don't see anything there. It goes up into the atmosphere until the cloud or the moisture hits an air mass up there that's quite a bit cooler than it is on the surface of the ocean, and now you form little droplets. The clouds form when the air masses are cooled to the dew point where the moisture goes out of being a gas and goes back to being a liquid, where it condenses again. It's generally cooled by upward movement. Convection is upward movement when the air is warmed and hauling the moisture upward. That's convection. Warm air rises, picks up more moisture, rises, picks up more moisture, rises. That's convection. The other way it cools is when it comes in off the ocean. Now think Pacific. Think that specifically. Oh, here comes a telephone. I'll have to try to remember who the telephone is. Can anyone remember who the telephone is? Is it Brianna? Who is it? Brianna, I thought it was. Okay, great. Good to have you. Okay. Let me just make sure nobody else has come in. I'm getting pretty good symbols now. Okay, I've got 11 people here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So one person that was here has checked out. Hopefully they'll be back. Okay, Brianna, we're just starting in chapter 13. This is only the maybe third or fourth slide. We're on, and if you got the book open, it's page 575 in the big book. If you got the little book, it's 23-3, the third page in chapter 23. So we haven't gone too far. What we're talking about is the hydrologic cycle that was on the previous slide, and that basically is water evaporating off the oceans, going up into the air, not as clouds, as evaporated water, as a gas, okay? But it goes up high enough, that's convection, until it hits a cool air mass, and where that happens, then the water starts condensing, forming little droplets. That's what the cloud is, okay? Now, cooled by upward movement, the other kind of upward movement is that cloud gets blown, or the water gets blown in off the ocean and hits a landmass, especially if that landmass goes up really steeply, like a mountain range. And the higher you go, the cooler the air is, and that mountain range. And by the way, most of the time land, especially in the summertime, I've got it backwards. Land can be a different temperature from the water was, especially the ocean water. Okay, so therefore high in the mountains it's going to be a lot cooler than it was down there. So there you form clouds over the mountains, and you'll see that often. Now the picture we looked at the very beginning had the clouds all over the ocean, which is where they came from, but there weren't any mountain ranges around there either. Had there been a mountain range, then you'd see the clouds forming on the windward side of the mountain range, coming off the ocean, and the clouds will form near those mountain ranges. There weren't any mountain ranges in California and in Florida, southern Alabama, southern Mississippi, Louisiana, and that part of Texas. No mountains there at all, so you didn't see any barriers like mountain ranges. The other way the clouds form are when you have colliding air masses with different densities. And not just different densities, that also translate to be different temperatures. So if you have a warm, moist air mass coming up, say, out of the Gulf of Mexico, hitting a cold, dry air mass that is coming down from Canada, say, then you get these droplets form right there, and that's where you have some really, really severe weather sometime when that's happening. The cloud formation depends on the atmospheric stability, and that is a tough little concept. I'm not particularly keen on the way the book describes it, though they're correct, and I think the slide set is even poorer than the book. But here's what we were talking about there. I can't get it to advance until I click on the slide. Now we go. Here's what we mean by atmospheric stability. A stable atmosphere, now there's some things here that sounds a little bizarre, and you just have to kind of know what they're talking about to understand what they're talking about, which is kind of going things backwards. What if you have a parcel of air that's moving up? Okay. Now, if that parcel of air that's being blown up is cooler and therefore a little denser than the surrounding air, it's going to come back to the level where it's more comfortable. Okay, because it's cooler and denser, it's going to want to come back. So it does that. That's a stable situation. Now, when we used to go for the lab for this class, for this chapter, to Channel 13 weather station, because I go to church with Jerry Tracy and ask him if we could come, and he's invited us just about every term. When I tell them it's time, unless they have some severe weather or they've got something really big going on that they can't have a crowd in there. But now that COVID's hit, no more tours of the station, so we can't do it. Sorry about that. But when he used to say this, he said, it's sort of like me now. I don't know. Jerry and I are fairly close to the same age. I'm probably a little older than he is. But we both know who Arnold Schwarzenegger was. Y'all know who he is? He was one time Conan the Destroyer or something like that. He was a movie star, played in the big action movies and stuff like this. He was a former Mr. Universe. He's really very strongly built, you know. Also a former governor of California, by the way. And I think he's the one who took over The Apprentice after Trump became president. You know, that's Schwarzenegger. Okay. Jerry used to say if he were to try to lift Arnold Schwarzenegger over his head, that would not be a stable situation. But probably Arnold Schwarzenegger, being a former weightlifter and Mr. America, Mr. Universe, he could easily lift Jerry over his head, or at one time he could have. That would be a stable situation. So if the air mass is cooler and denser than the surrounding air, then it tends to return to its original level without incident. However, the unstable atmosphere, and I'm sorry that this square is in the way, I bet you it's blocking what you can see. It's so bizarre. That blocks what you can see, right? Now it's fading out. These blocks over here, you don't even notice are there. Why can't that block be like these so you don't notice them? It'd be in my way, but it wouldn't be in yours. But this is in everybody's way. Okay, the unstable, when the lifted parcel of air is warmer and less dense than the surrounding air, then it tends to keep on climbing. Okay, it continues to rise, and this creates what they call the thermals. Now, in some part of my mind, that says, well, that sounds like that's stable because it's going where it wants to go. But no, that's not stable because it's ultimately going to cool. And when it does cool, then all that moisture that it may have carried up there is going to collapse, okay, and come down as precipitation, and sometimes violently. So that's what they mean by an unstable atmosphere. Now here's how they represent it on graphs, okay. Now what they have here is increasing temperature in this direction, increasing altitude in this direction. So the air mass is going up, okay, but the temperature of the rising parcel of air is less than the temperature of the surrounding air. So gravity is pulling it downward. It's happy to hang around and move downward. Okay, that's stable. That's exactly where it would tend to go. Its temperature is less than this, so when gravity is pulling it downward, it's going to be very happy to come down until it reaches its equilibrium. That's a stable situation. That's how things ought to be. Okay? Now, an unstable situation would be more like this. The temperature of the rising parcel of air is warmer than the temperature of the surrounding air, so this parcel just wants to keep climbing. Well, you know it can't keep climbing forever. It's going to hit some place of instability, and that's where things happen. Now, these graphs don't communicate that to me, but this is the general idea here, that this is going to try to keep rising, and at some point it will then become unstable because it keeps going up until it can't support the moisture that it's carrying, and that's when it becomes unstable. Okay, that's a real quick and dirty there about atmospheric stability. I don't think the previous chapter is going to give you much clarity on that, but you can go back and see. So that takes us over pretty much to page, I think 576. Okay. Now, it may still be partly on 575. This is, okay. The rising moist air cools, eventually reaches the dew point. When that happens, the droplets condense, because that's what's happening at the dew point. You get cool enough so it can't support the moisture in the air any longer. So they condense. Now, they have to have something to condense around. They just don't automatically condense. They find some condensation nuclei in the saturated air. Okay? Now, if there's none of those in the air, which usually are, but you have supersaturated air, and that could really be a tough situation, because then when it does start happening, it's going to come very quickly. But most of the time they do have them. Now, what are those condensation nuclei? Sometimes they're as simple as just dust particles. Okay? Sometimes they could be ice crystals. That's a very common kind. Sometimes they could be, they actually, give the example of salt crystals. And it's sort of hard for me to imagine that, except that water evaporates out of the ocean so rapidly, it may actually take a little crystal of salt up with it. Most of the time that's pure water coming out, not the salt crystals. But if they do pull some up, then you could have salt crystals as well. Some sort of thing for the condensation to happen around. Okay? Now, the cooling of that rising air is slowed down a little bit by release of the latent heat of vaporization. Now, that was something covered in the first half of the book, so I don't know if that means anything to you, but let me explain it this way. I bet you every one of you has put a pot of water onto the stove to boil, haven't you? Or to heat up. You turn on the heat, gas, electric, whatever you've got, turn it on, and the first thing that happens is the water starts warming up. And it may take a while, it depends on how much water you got there, how high you got the stove turned, the water warms up. But after a while, the water has warmed up hot enough that now it begins to boil. And I don't know if that's someone coming in. I don't think it is. No, it's not. That it begins to boil. Okay? And I don't know if you know what boiling actually is. That's water inside the water that's now turning to gas. It's gotten hot enough to go from, oh, here comes Kenda. That's who left, and she's coming back now. Okay. I already got her in the book. I want to make sure I do. Yes. Okay. She's here. Okay. So what's happening then when water begins to boil, it's gotten enough energy from the heat on the stove that it's changed from a liquid phase to a gas phase, and now that's what makes it boil. That's what makes it bubble like that, is the fact that it's changing from a liquid to a gas. Now, here's something I don't know if you realized. My wife has gotten really into canning preserves. It starts with strawberry season. That happens really early. If she can get some really good strawberries, we usually put up a batch or two of strawberry preserves. And then once the peaches get here, she'll put up peach preserves. And this year we had just the most pears on our pear tree we've ever had, because we had such a wonderful year of rain and everything else, and it was warm this spring. It didn't freeze the blossoms. We had a bumper crop of pears. She put up pear preserves. Over in Georgia, we had a few blackberry plants we put up. They produced like crazy this year. She put up blackberry preserves, and then in between she's sometimes done apple butter and whatever we can get, fresh fruit. She did cherries one time. I'm benefiting from that because she's trying not to eat that much, so I'm eating as much as I can and get away with it. So anyway, but what we do when we're putting up the preserves, we watch the temperature rise. It does start boiling, but when it starts evaporating out the water, then the concentration of the sugars in the water increases the boiling point, and she has her thermometer she puts in there, and it goes well above 212. It goes to 214, 215, I think somewhere around 216, 217 or something. When it gets to that temperature, that's at the right concentration. So what is happening there, all that time you're adding heat, the water heated up pretty quickly. Once it started boiling, it did not increase temperature at all. What it did was use that heat to change from liquid to a gas. That's called latent heat. Latent means hidden. It's a hidden heat. You don't sense it in temperature, you sense it in change of phase. Well, when the cooling air is slow, the cooling of the rising air is slowed because the latent heat of vaporization, that goes the other way too. They often call it latent heat of condensation. When you go out of the gas phase back to liquid phase, it gives off heat, just like it got heat, gathered heat when it went from the latent heat of vaporization from a liquid to a gas phase. It releases that heat when it goes from a gas to a liquid. Doesn't change the temperature, but does change the phase. Let me see if someone else is coming in. Nope, still the same group. Okay, now that release of latent heat of vaporization actually slows that cooling process. So now it hangs around there a little bit longer. It's still coming out of solution. So what happens is huge numbers of droplets appear, and that's what we see as clouds. Okay, now I'm looking out my window right now, and it's a fairly cloudy sky, and most of the clouds I see are fairly bright white, and that's because the direction I'm looking at them is actually reflecting the sunlight off those water droplets. Sometimes those clouds, like that very first picture we showed, really dark. That means the sun is overhead and the light's not getting through. It's all being reflected back up, and that's what makes that same cloud, if you're underneath it, looks dark. Up above it, it would look bright and white and fluffy. Okay, so that's what's happening. So usually when those really big storm clouds roll in, they block so much of the sunlight that they get very dark looking, and you don't realize how thick they are, and what we see at the bottom is basically where no light or very little light is getting through. That's why they look so dark. So that's what's happening. Huge number of droplets finally appear as clouds. So that's the cloud forming process. Now I won't advance until I click on the slide. Okay, here we go. So where does precipitation come? Now, before we get there, example 23.1 and 23.2 are here in your book, and it's basically talking about that latent heat of vaporization, condensation, those kind of things. This is all from chapter 4 at the beginning of the book. We haven't done it, so don't sweat this, but if you want to at least read through it and get an idea of what's going on, I think you'll see it makes some sense. It's not just blah blah blah. Okay, look like someone else is coming in, but they're not. Okay, so let's move on to the origin of precipitation. What is precipitation? It's anything falling, coming out. If you were hiking on a glacier, they have big cracks in the glacier they call precipices. Okay, things you could fall into. You don't want to, okay? You don't want to fall into one of those, okay? That's what it means. Precipitate means to fall out, basically, okay? Well, what we have here is water falling out of the sky, returning to the Earth's surface, okay? Now, rain is when that's liquid water. Snow or hail is when it's solid water. Those are actually ice crystals coming out or chunks of ice. Now, remember when I was talking about when we had the tropical weather here, lots of moisture coming from the Gulf, and here comes Denisha again. I think she's already been here. Yes, she has. So she was one that we lost, and she's coming back. Okay? When those events were happening, when we had lots of moisture here, and I said in the morning, if it got cool enough that night, you might find heavy coats of dew on your windshield, on the grass, or wherever, outdoor tabletop or something. In the wintertime, that will show up as frost. That's not precipitation. That didn't fall out of the air. That was air that had that high level of moisture in it near the ground, near the surface. That's a surface process. And that air cooled as the ground cooled, as the grass cooled, as your windshield cooled, and that's where the droplets came on that. That's not precipitation. It is moisture, but it's not precipitation. So precipitation doesn't mean moisture, it's things falling out of the sky. Now, precipitation forms in two ways. Okay? Now, the first of these is when you have those little bitty water droplets way up in the cloud, may have formed around condensation nuclei or whatever. They formed up there, and then the air either continues to cool or there's more moisture coming in, and the coalescence of cloud droplets. This big old droplet bumps into this one and they coalesce to be a bigger droplet. And then they do and pick up a few more and stuff. They get big and heavy and then they fall out of the sky. Now that happens mostly in the tropical areas because it happens frequently there, it seems like. My first full-time duty station, here's Diana coming in. I don't think she's been here today yet, has she? No, she hasn't. Let me mark her present. Okay, good deal. Good to have Diana here with us. Okay, so my first, after I graduated from school, went into the Navy, my first orders, I was to drive to the West Coast, or get however I wanted to the West Coast. From there, check in, and they were going to fly me to Guam to pick up my first ship because it was coming back from a Western Pacific deployment. This was right at the end of Vietnam. And it had been a very tough deployment on them. I was coming in at just a really good time, right as Vietnam was winding down was when I was going in, which was just the luck of nature, just my good fortune. Okay, but the ship was actually in the Philippines, but they weren't absolutely certain whether I could catch it there because it was due to leave about the same time I would have arrived, so they flew me to Guam. Well, it took several days, in fact pretty close to a week, for the ship to get to Guam. And there I was stuck in the middle of this island, Guam, very tropical island, Guam, and they put me in a BOQ up in the middle of the island where not near anything else, and there was absolutely nothing to do. It was expensive taxi. I hadn't gotten my first paycheck yet, so I couldn't spend a lot of money. So I just had nothing to do, so I would just take off and walk just to get exercise and just explore around that part of the island. And it never failed. When I got just about as far from the BOQ as I thought I would probably go that day, here would come a rainstorm. Not a storm, it just rain. And that was coalescence of cloud droplets. Enough moisture came in off the ocean, cooled over the cooler land, and it rained. And the only days it didn't rain were were days that it rained twice. You know, I would get soaking wet, head back to the BOQ. Before I got there, the sun would come out and I'd be dry again. You wouldn't even be able to tell that I had gotten wet. It was just incredible. It was very tropical. What happens around here more frequently, believe it or not, even though we're pretty far south, now we probably do get some coalescence droplets in our rainfall, but most of it comes from ice crystals. And what's happening there, let's talk about the coalescence process. This takes place in warm cumulus clouds near the tropical oceans. Like I say, Guam. That was right in the middle of the very warm tropical Pacific. Okay, the Philippines did the same thing. Okay, later I was there on later deployments. The clouds, and they say here, contain giant salt condensation nuclei. And when they say giant, it's not big hunks of salt. No, that doesn't make sense. But it just means little crystals of salt that are bigger than the other crystals of salt. Okay, just bigger than normal. And of course, salt will attract moisture because salt dissolves easily. So that's what forms the condensation process. Now the icicle process, that's the one they're talking about here, this occurs in clouds at the middle latitudes. Now sure, we're in the southern part of the middle latitudes, but we're still in the middle latitudes. Here's what happens. Rather than salt crystals being the condensation nuclei, it's the ice crystals. Okay? If you go far enough up in these clouds, you get to cold enough air up there that indeed you run into ice crystals. So these ice crystals that are already hanging around way up there, they capture these water molecules as they're being convected upward, and then the water molecules attach themselves to the ice crystals, and what happens, the ice crystals tend to grow and grow, bigger and bigger, until, hey, they get so big and heavy, the cloud can't support them anymore, and they fall to the ground. Now, no, they fall. They precipitate. If it's wintertime and you're far enough north, they fall as snow crystals, ice crystals coming out. The air temperature near the ground has to be very close to freezing point or below freezing point, and that's when you get snow. We very seldom have air temperature that is cold enough that when these things are falling, they will actually fall as snow. It has happened a few times. I can remember a couple of really big snows here in the southeast, but they've been decades apart. Okay, it's not a common thing. Last winter, I don't think we had a single snow of any mention. We may have had a few flakes once or twice, but that's all. I don't think the year before that I remember any snow. It's been several years since I remember what I would call a significant snowfall here in the southeast. What happens with us is these big ice crystals get so big they start falling, but as they fall, they hit warmer air and they start melting. And as they melt, they form these big old water droplets. And I think I mentioned before, I can remember in summertime sometime driving to North Carolina to see, I wasn't driving, my father was, driving to North Carolina to see the family. Just all of a sudden this great big old raindrop would hit the windshield. You know, you weren't even anticipating that happening. It'd be big and it would splat and make just a big mess. That's what one time was, an ice crystal way, way, way up there, and it melted on its way down, and by the time it got near the surface, it was going fast enough, but was big enough it just splashed. Okay. That's what we get most of the time. It was ice crystals way up in the clouds. By the time it reached the surface, it was rain. And that's one reason rain almost always feels so much cooler than the air is. That was one time an ice crystal. It wasn't just warm water, okay? It was an ice crystal that has been warming up on its way down. Okay, can't advance until I click the slide. Okay, now, toward the bottom of page 577, 23.2, what are your weather producers? Now, we've already talked some about this, and here we'll launch into it a little bit more. I wish I had a globe here in front of me. If we were in class, I'd have the globe out there and you'd be looking at it, but I'm not. And we have a big old globe downstairs, but if I held it up, it would take up the whole window here. Okay, so don't have anything used to handle. But think of the region around the equator, 10 degrees north and 10 degrees south of the equator. This is the amount that gets the most direct solar radiation year-round. Okay, 10 degrees north, 10 degrees south. Sure, the tropics are 23.5 north and south, but they're on the fringes there. This band right there, that gets most of it. What happens? The air heats up, of course. It rises and spreads ultimately to the poles. What happens when it's doing that, when the air heats up, rises, spread toward the poles? That leaves a low pressure area right around the equator, between 10 degrees north and 10 degrees south. Okay? The air cools as it spreads to the poles, and as it does, it moves back, becomes more dense, because the warmer something is, the less dense it is. The cooler it gets, the more dense it is, because it takes up less space. Same air, less space, that's denser. Okay? So the cools, becomes more dense as it rises, starts sinking back to the surfaces at latitudes near 30 degrees north and 30 degrees south. Hey, that's where we live. Remember, we're 33 degrees, 23 minutes, and 45 seconds north. We're just in the upper part of that band there. Okay? So in there, you typically have a band of fairly high pressure. Okay? Now, in my other physical science class that some of you are going to be part of in the second mini-term, we will actually do an experiment that I will be, well, I don't know if we can do this one. This one requires us to be on campus. But not at all surprising, if we did something, I would ask you to give me the barometric pressure at that time. When we were on campus, we always did this. Someone would pull it up on the phone, find out the barometric air pressure, and I was shocked at how many times that came back right at or above 1 atmosphere of pressure. I thought, wait a minute, we're north, we're at a higher elevation, we shouldn't have a full atmosphere of pressure. We should be slightly less than that. But no, we're not, because we're in this band, or in the outer edges of this band, where you have extra high pressure areas. Now, what happens then? The end result of this stuff happening, band of low pressure near the equator and bands of higher pressure 30 degrees north and 30 degrees south of the equator, right below where we're living. Okay? So what you have is low pressure here, high pressure here, low pressure here, high pressure there. Okay? And that produces large convective cells to equalize that pressure. Okay? And basically the low pressure areas are sucking air into it. The high pressure areas try to push air away. Excuse me, my head is clogging up. I'm having trouble breathing. I think it's the falling temperature. Oh, I meant to ask this question early on. Time out a moment. What is today? Does anyone know? We talked about it in a few earlier chapters. The autumnal equinox. You got it. My wife looked it up this morning. I asked her, I said, have you heard when that is? And she looked it up on her phone, found out it was 8:30 this morning. The sun was crossing, the sun's ecliptic was crossing the Earth's equator 8:30 this morning. That was right about the time my first class started. So that was, at that moment, everybody had equal day, equal night. Well, I mean today, basically, equal day, equal night. Same number of North Pole, South Pole, everywhere in between. 12 hours of daylight, 12 hours of darkness. Okay? And this morning, it's been sort of nice. I usually wake up when it gets light outside, and so this summer I was waking up pretty early. Okay, this morning I slept in a little bit longer because it just didn't seem to be quite as early, closer to 6 o'clock. Not right at 6 o'clock, but closer to it when the sun finally came up. Okay, sorry that was off the subject, but stuff we had talked about. So you get these large convective cells that form to equalize the pressure. What that means, and there's other things involved with it, low pressure areas, especially in the northern hemisphere, tend to rotate counterclockwise. High pressure areas tend to rotate clockwise. Okay, and this sort of equalizes the pressure. Okay, these are what do it. Okay, now I can't get this to advance. Now, other weather producers, besides the fact that you have, yes, was there a question? Okay, I think someone's microphone's on. Okay. The other weather producers, besides just the normal thing, and by the way, let's go back to that again. What do we call these low pressure areas near the equator in the summertime? We've just had several of them pass through. They start off as tropical depressions, and they'll move up to tropical storms, and they may move up to hurricanes. And then if they hit land, they tend to drop back down to being tropical storms and ultimately back to tropical depressions. That's what produces hurricanes. Low pressure near the equator, high amounts of energy, because in the summertime, north of the equator really is getting hit by that direct solar ray energy, and that's what forms. Oh, yeah, here we go. Sancho is here. Let me get Sancho here. Okay. Good deal. We're getting to be a pretty good number today. That's good. So in the summertime, these high energy, lots of solar radiation, low pressure here, and as they drift northward, that low pressure tends to start moving in that counterclockwise flow, and if it's enough of a drop of pressure, then the winds increase in speed. That's what forms a tropical storm. Increase with that, more and more drop in pressure in the middle, that becomes a hurricane. And that's how they measure the hurricanes. We'll talk about that later, is by that pressure difference. Okay? So that's the result of these kinds of things happening that we see is hurricanes and tropical storms coming through. And we've just had, seems like several. They're now they've been all the way through the alphabet, and now they're in beta, or maybe even past beta now in the Greek alphabet. All right, so another weather producer, air masses. What an air mass is a large, horizontally uniform body of air. This whole body here, horizontally uniform. Everything in there is about the same. Most of the time, the moisture and temperature conditions are nearly the same in that whole mass of air in this horizontal body. Okay, it's not a physical body, it's a bunch of air. Now, four main types. Okay, the first of these, the continental polar. Okay, now what does that mean? that means you have it coming in the northern hemisphere. And let's talk about the U.S. because that's where we live. This would be what we call, you often hear the weathermen say, a Canadian air mass. Continental polar. It's coming off continental areas, off land area, coming from, for us it would be the North Pole, heading south. Okay? Well, sometimes they won't call them a Canadian air mass. If they're really cold, they call it a polar air mass. Okay? And that's what they mean, continental polar. Now, if it's coming from the polar regions but coming over water, we call that a maritime polar, which you can get either off the Atlantic or off the Pacific. Coming from the north, coming down, bringing that cold, this time sort of moist air. This would usually be cold, drier air because it's coming off land. This is cold, moisture air because it's coming off the water. Maritime polar. Or we could have continental tropical. Now, we don't have that much continent below us, mostly Mexico. So for anywhere from the tip of Texas here to the edge of California here, that's coming off Mexico. That's continental tropical air mass. They're usually warm air masses, but tend to be very dry air masses. The maritime tropical, and that's what you get off the Gulf of Mexico, thank you very much. That's what keeps us wet. Off the Atlantic, sometimes the trouble is they come in from the wrong direction unless you got these tropical systems coming in, and they will hit. And sometimes they hit Florida, Georgia, South Carolina, North Carolina. A few of them have hit as far north as New York, New Jersey, and those areas. Those are maritime tropical. On the west coast, coming off the Pacific. Now, you would think they had more of this here than you would have back here east, but actually, even though the predominant winds are from the west, sometimes these are cool masses of air that are coming down pretty far south. In fact, San Diego, California is way far south, but it tends to be quite pleasant in temperature. Not nearly as hot as we are here. Part of that is the ocean acts like an air conditioner for it, but the other part of that is that the currents, and we'll talk about that in the next chapter, so hang on to that. Okay, so those are the four big classifications of air masses. These dictate what they call air mass weather, of course, okay? The weather conditions will remain the same over several days. Let's see, is somebody else coming in? I don't think so, but let me check. Nope, don't see anybody. Okay. Now, I don't know exactly what's happening now. My guess, continental polar air must be making its way south because this is cooler than early September or mid-September. Well, actually now in late September usually is. We're beginning to feel the effects of this. I have a feeling in a few days we're going to warm back up, get a little bit more moisture in here. But I think what we've been experiencing for the last day or two is a continental air mass coming down from Canada that's really cooled us off nicely, pleasantly. Okay? And as you see, we've had like 2 or 3 days of this. So that sort of supports the conjecture that it may be coming from a continental polar air mass. Okay? Now, what happens, weather changes when the new air mass moves in or when the air mass acquires local conditions. Our local condition now would be a little warmer than this. If this air hangs around too long, it's going to warm up and become more typical. But more likely, we're going to have a stronger system come up from the Gulf of Mexico, and that's going to have moisture in it. And I believe, if I'm understanding what my wife said, I think around day after tomorrow, Thursday, maybe the day we meet again, we are supposed to have a pretty rainy day. That supports the idea that you have some maritime tropical air mass that's going to start pushing against this continental polar air mass that has come down from here, trying to push it back north where it belongs, okay? And this warm, moist air is going to cool and drop a lot of rain on us. I think Thursday we get the rain, Friday Georgia gets it. I think what you were saying, because we're scheduled to leave Friday morning very early to head over to Georgia. That's where I grew up, and that's the farm I grew up on is over there. Both of my parents have died, and so the farm was split among the four of us children, and my two brothers and my sister all live on the farm. We're the black sheep. We moved to Alabama, you know, foreign country here, but we're going back because I have to take care of some stuff. The grass, all the rain, they got, I think, better than 7 inches of rain, and that last thing that we got, just a quarter of an inch up here, it smacked right into the farm here, and they got a lot of rainfall. So the grass is really growing, so I've got to go over there and sort of take care of some things. We also planted trees. We're no longer doing beef cattle and grains and things like this. We're doing tree farming now, so got to go do some things with that. So anyway, hopefully the rain will be ahead of us. We'll follow it there and have some fairly decent weather while we're there. Okay, but that's illustrating what's going to happen. I think a maritime tropical air mass is going to start pushing up, pushing against the continental polar air mass that we've got hanging over us now, and when that happens, we're going to get rainfall. Probably a fair amount of rainfall. I can't get it to advance until I click on the slide. Okay, now that leads to weather fronts. This is on page 580. Okay. Basically, the boundary between those air masses at different temperatures is what we call a front. Now, what we had come down probably a few days ago was a cold front, because it was pushing cold air ahead of it. What we probably are going to have coming up in the next day or two is the warm front coming up out of the Gulf, pushing against that cold air mass. That will be a warm front. Now, what occasionally happens is the two fronts sort of are equal to each other, and they sit over you, and those are the days you just get rain and rain and rain. It's stationary, and everything is just landing on you. Other parts are not getting anything, but you're getting the bulk of it. So the cold front is when the cold air masses pushes into and displaces the warmer air upward. Remember, the warmer air is less dense, so when the cold air comes down, it pushes the warm air up. Think of that. That is your unstable situation. That's why we're probably going to have some pretty heavy rain on Thursday. It could be, if it happens quickly enough, if the differences are enough, it could be maybe some fairly violent rain. By the end of September, though, we're out of most of our really bad weather time frame, okay? Hopefully we won't have too much of that, okay? The moist air that rising is cooled, leading to large cumulus and thunder clouds. We could have some thunder. I don't know if they're predicting it or not, but I do think they're predicting a lot of rain. Now, the warm front, however, is when the warm air advances over the cooler air mass, and when they say over, it usually is over that. And and by the way, this is a warm front, so this is a long, gently sloping front, and now I can't read this, something in rain. I'll have to wait till that box gets out of the way. It may form in advance of the front. So actually that rain we get on Thursday may be leading to warmer weather over the weekend. So clouds and rain may form in advance of the front. This, I think, is what's going to be happening on Thursday. That's why I don't think it's going to be severe weather. It's going to be much gentler. The stationary front, the forces influence the warm and air masses become balanced, and then they just sit there and compete with each other. Maybe one pushing this way a little and one pushing that way. And that happens occasionally when you just have a week or more. It just seems like it never stops raining. Never rains hard, but you get a little rain every day. We had several of those this year, it seemed like. So here's the illustrations of what I'm describing. Now first, this is a busy map, and they haven't really taught you enough to understand it completely. But remember I said the low is when you have the low pressure areas when the air moves counterclockwise around this in the northern hemisphere anyway, moves like this. So it's bringing warm, moist air up here, hitting against cooler air here, or brings cooler air down and it goes into warmer air here. So that's what a low pressure is going to do. Now, today in lab, we're going to talk about areas of equal elevation. Those are called isoclines on a topographic map. These are areas, these lines here are areas of equal pressure. These are called isobars. Iso means same, so it's same barometric reading all along that line there and along this line here. That's 100, I can't read it now, 1,000, no, I can't read it. It's off. Here's one. Where's one I can read? But anyway, this is bringing the air in this direction. So behind this front, you have cold air being brought down by this strong low pressure area. So this is a cold front moving this way. That's a cold front. Over here, you have high pressure turning clockwise. Now this is a very weak high. That's a pretty strong low here because these isobars are really close together, meaning you have a good wind gradient between those. This high pressure is just really, really weak here, but it is turning clockwise, so it's bringing cool continental air down, so this is another cold front. This is more than well, both of these are cold fronts. In the middle here is another low, again a very weak low, and right here, because it's turning like this, you probably either have a stationary front or a warm front right in that close proximity to the low. Okay? This is not a very active weather map, so it's really hard to pick too much out of it. Here's a high pressure. This is because the lines are a little closer together than these are. It doesn't have many lines at all, but this high pressure area turning clockwise, that's going to be a cold air pushing this way, so there's a cold front, but pulling up warm air in this direction, and that produces a warm front. And that's the symbol for a warm front. Okay. That's the best I can do with what they've given us here. The picture in the book does a little bit better. Of course, it's not an actual weather picture. It's an idealized thing, but I'll let you see that as well. It doesn't show the fronts here, but it does show the high pressure, and you see as you get closer here, I can't read those. Is that 1038? No, 1028, 1032, 1036. So it's getting higher as you go toward the center, and all in that circular region there, the curved region, all the barometric pressures are the same on those lines. So your high is in the middle. Your low down here, notice it's dropping as it gets closer to the low. 1016, 1008, 1004, and 1000. Okay, dropping as it gets closer to the low. Okay, so that's the difference in a low pressure and high pressure. Now, the low pressure would be going counterclockwise. I hope I'm going right. I'm backwards here. No, that was clockwise. This is counterclockwise. Counterclockwise here. So it's bringing warmer air up here, bringing cool air down here. But this is going clockwise. So it's bringing cool air here. So this region in here, you're going to have very large amounts of wind because the barometric pressure lines are real close to each other. Very stable out here, not very much wind at all. Now, I don't know if you'll ever see one that's exactly like that, but that's the general idea. Okay. Now, this actually fit better on the, no, this fits well here. Here's the cold air mass pushing its way in. The warm air mass was sitting here. It's getting forced up here. Cold air mass comes in. Now notice how abrupt that is, because the cold air is denser and it's forcing its way in. It's sort of like a bulldozer, like we talked about the glaciers, only it's moving faster than that and pushing there, forcing the warm air over the top. That's your front. Cold on this side, warm on this side. The cold air is pushing this way. That's called the cold front. Looking down from above, excuse me, looking down from above, this is what it looks like. The cold front is pushing its way here, forcing the warm air up top. You can't see the warm air moving up top. Okay? Now, there's supposed to be one of the warm air, but we're going to see that in a different one. So let's go on to that. Okay. Seems like there should be another one there or here, but they're not showing up. Here's what's happening. Now get the scale of this. Cold air coming in here. Warm, moist air is here being forced upward. And as it's forced upward, it goes into these big, tall cumulus clouds. That's what cumulus cloud typically has, a hat on it like this. One side or both sides. Typically that's it. Huge towering clouds. Now notice this altitude here. Going from 0 to 15 kilometers, that would be about 9 miles up. Okay, is this somebody else coming in? I don't think so, but let me check. No. Okay. 9 miles up. Going up 9 miles, I guarantee you there's ice being formed in here. Guaranteed there's ice up here at these high elevations. All this moisture is being sucked up here, and these usually form counterclockwise flow and pulling the air, warm moist air up because it's trying to rise. It's going to cool and condense, and that's what forms the instability. Quite often the rain is ahead of the front or right on the front. Okay. Now, these happen a lot in the summertime. Those tall, huge cumulus clouds. If that is sucking up enough warm, moist air and building those ice crystals bigger and bigger and bigger, they start to fall and then they hit more air coming up. It forces them up again. They cool again, get bigger and bigger every time they make a transition upward. Ultimately get so big they fall, and if they don't melt before they hit the ground, that's what we call hail. In the summertime, sometimes even in the spring, you can have these big major hailstorms that happen at the same time you're having these severe thunderstorms. They happen together because they're coming out of the same source. Okay. I don't care for hail at all. It's sort of fun to watch it, but it really dents your car. It can damage your roofs. It can damage fruit, crops. Hail is not my friend. Okay. Rain, I can handle rain. I don't mind rain at all. Hail, it does too much damage. Okay. Now, so there's your cold front moving in. Let's see how that compares to a warm front moving in. The cold air was already in place, but the warm air is coming from the south, and it builds some cumulus clouds. But look at these clouds. They're barely 4 kilometers, 5 kilometers high. That would be 2.4 to 3 miles high. As before, they were 15 kilometers high, you know, way, way bigger. These will produce rain, lots of rain, okay? And a lot of this rain will be ahead of the front itself. It starts raining early because that warm air is going up over the cold air, not so much pushing it out of the way, though it does push on it some, but it climbs up over it, it condenses, and it rains over the cold part, okay? And this will be happening when, this I think is what's going to happen when, say on Thursday, that warm, moist air from the Gulf climbs up over on top of the cold air that has been sitting on us for a few days, and that's when we're going to get that usually gentle rainfall. There could be some thunder in it. Cumulus clouds will cause thunder sometime and lightning, but usually it's not too bad. The warm front, the warm air masses, the warm front usually are less severe. Number one, the gradient is less, so it takes more time for the moisture to happen. It falls ahead over the colder areas, and then it's followed up by nicer weather. Now, if you had studied the atmosphere first, cirrus clouds are the little thin clouds, wispy, really high clouds. These would be cirrocumulus clouds, I think they call them, and these are the cumulus. Just if you ever run into those words, that's what they are. All right, I don't think they have a picture of stationary front. So we're moving from there into, okay, my watch's battery is just about dead. I'm going to have to take it down and charge it between class and lab time. Waves and cyclones. This starts on page 582. Now, they mention the term waves, but really don't do a good description of it. I can remember when I was working for Southern Research Institute, which is here in Birmingham. We were doing a radon study down in Florida, Central Florida, around Lakeland and Bartow area. And we had set up this experimental, actually another company had built it, but we were managing the study of it. And we had put all sorts of weather devices around it. We had put things to measure radon levels. We were measuring lots of things that were going on down there. And what we had happen one day was absolutely confusing. Radon levels had been, you know, so-so, and all of a sudden they spiked. I mean, they just went through the roof. And we had also, like I said, we're getting weather data, and it had been fairly tough, and suddenly the pressure dropped like crazy. Wind speed went up like crazy. And it was just so unusual. And we thought, why did all of our equipment go haywire at the same time? Did we have, you know, electrical problem? What is going on here? And so I called Jerry Tracy to see if any of this made sense. He said, yes, what you had was a tropical wave come in. And that's an area of low pressure, very low pressure, that came in not circular, but basically linear. And that's what came and hit. And when the pressure dropped, it sucked the radon into our building. You know, we thought we had built the building pretty solidly, or the previous company had, but it sucked that radon right into it. And we found out that's a really big driving force sometimes. Fairly temporary, but it still was. So that's what a wave is. It's an area, usually tropical area, coming in, and this was far enough south in Florida that they were technically not in the tropics, but it was coming in from the tropics, and that's what dropped it. So here's the mechanism. You have a bulge or a wave often formed between oppositely moving air masses. Let's see if they give us a picture here. Now, parts of their illustrations don't really make sense to me. Okay? And part of it is they don't list what they're doing here. When I look at this, I think the air near the ground is warm air and the cold air is up here. I don't think that's what they mean here. I think they mean you have warm air on this side, cold air on this side. This cold air is probably moving in one direction, whereas the warm air is moving in the other direction. Now, if they do mean this is a vertical thing, that is a really unstable situation because the cold wants to come down and the warm wants to go up. Okay, but what I think is happening here, this is side-by-side stuff. You have cold air up here, warm air down here, and they're moving, and they're moving in sort of opposite directions, okay? Oppositely moving air masses. So bulges or waves often form between these matches. This is what it means, okay? The warm air that was coming this way is trying to move upward. The cold air moving this way is trying to move downward. So this is your cold front on this side, okay? And your warm front on this side. The warm air is trying to push over this way. Cold air is being pushed, is coming down this way. Again, not a great illustration in my mind. Okay? Now, the overriding uplifted cold air produces and when they say overriding, that means it's vertical then. So I can't quite make sense of it. Uplifted cold air, you wouldn't think it being uplifted because it tends to fall, okay? Produces a low pressure area. That makes sense. If this cold, denser air is moving up, it's leaving low pressure behind it. And if you are leaving low pressure behind it, that is going to create a problem, okay? Further cold front motion leads to an occluded front. So this is your cold front in this direction. Pushing this way, the warm front is pushing this way. If that continues, you have the low pressure here, and the cold air is coming down this way, like it was here, and the warmer air is pushing up this way. And this, you see, you start having circular motion here, okay? And this is what they call the occluded front. And I'm going to read this to you from the book, in case you don't have your book open. This is on page 582, right-hand column, near the bottom of the page. An occluded front is one that has been lifted completely off the ground into the atmosphere. The disturbance is now a cyclonic storm with a fully developed low pressure center. After forming, the low pressure cyclonic storm continues moving, taking the associated stormy weather with it as it in a generally easterly direction. Such cyclonic storms usually follow the principal tracks along the front. Okay, so basically that's what's happened. You had a cold air up here, warm air down here. They fighting with each other. They create this bulge. The warm air trying to push this way, cold air pushing that way. You get this. You begin getting circular motion. It becomes fully developed here, and there you have a low pressure. Okay. And that low pressure, depending on how strong it is, if it's just a weak low, it could just be creating some rainfall. If it's a really strong low, that could be a thunderstorm. If it's a supercell thunderstorm, that could become a tornado. Okay? You hear them talk about these words all the time on weather. Getting away from them now because we're getting out of that season. Okay, so the cyclone, this is advanced to the occluded front, form a cyclonic storm here. That doesn't have to be a cyclone, but just a cyclonic storm. The cyclone is a low pressure area with inflowing upward force winds. Because it's such low pressure, the winds come in and are forced upward. The low pressure is sucking it upward, and as that's happening, then you are, it's creating, and we'll get to this in a little bit, it's creating circular motion. And I'll go on and give you the word now. It's the Coriolis effect. We'll hit it later, but that's what's causing it, and that's what makes it go counterclockwise in the northern hemisphere. Actually, the cyclones would be clockwise in the southern hemisphere. And like I said, high pressure areas are clockwise in the northern hemisphere, counterclockwise in the southern hemisphere. Ah, here it is. It's right here. The circulation pattern is caused by the Coriolis effect. That comes mostly because of the spin of the Earth. At the same time, the air is moving up away from the Earth, and that creates this circular motion. Okay? That's the Coriolis effect. If someone hasn't chosen a paper topic yet, that would be a good one. Either who in the world was Coriolis anyway? How did he come up with this effect? What are effects of this? How does that affect weather? How does it affect anything? Just winds and all sorts of things. I can tell you it's a true story, but it's still sort of a dumb story in my book. I don't think I've told this one before in this class. I've told it in some class. I don't think this term yet. When I was an undergraduate at Georgia Tech, I was a physics major, and one of my physics professors that I had for sort of a low-level physics class was Dr. Goodness gracious, I've forgotten his name now. I just had it on the tip of my tongue and it lost it. Well, whoever he was you could tell he was a very bright guy. He wasn't the most exciting lecturer and that kind of stuff, but he really knew his stuff. Okay, and he was pretty good for trying to get students what they needed too. That wasn't always the case at a big school like that, but he wasn't too bad that way. Well, I found out later, much later, that he was a honcho in crystallography. That's forming of crystals, the nature, the physics of crystal growth and things like this. He was a honcho in that. In fact, he was at that time, I think, the editor-in-chief of the International Crystallography Journal, which was way up there, okay? And we found out, he was telling us that they had meetings. Usually they had them in Europe or North America or somewhere like that, but they had meetings one year down in Brazil, Rio de Janeiro. Now, I don't know if anyone has ever heard much about Rio, but it prides itself in being the party city of the Southern Hemisphere. Now, I don't know if people in Australia would go along with that because they consider themselves pretty hardy partiers, but here's Drew coming in. Good deal. Wondered where Drew was. Let me get Drew marked here today. All right. Now, I'm sure we've had some people coming and going. There's 3, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 15 people have been here. We currently have 14, so we have lost somebody, but hopefully they'll be back. Okay, so anyway, he was telling us this. He told us in his own thing that he was going to, and he wasn't telling us about Rio. I had heard this about Rio. He just said the meetings were in Rio de Janeiro, and we thought, oh man, those of us in the class, they thought that's quite the party city down there. Okay, beautiful city too, if I understand. I've never been there. Now, Sao Paulo is the biggest city in Brazil, but it's the business capital. It's a serious city. Rio is the party city. It's a big city too, and I'm sure they do a lot of things. But anyway, he was going down to Rio because the international meetings were down there, and he said, I just couldn't wait. And we just thinking, oh man, we're going to see a new side of this guy. I just couldn't wait till they got me to the hotel. I went up to my room, and I rushed in to the bathroom to flush the toilet. And we went, what? He was excited to be south of the equator, where that when you flush the toilet, the water goes clockwise rather than counterclockwise. He just couldn't wait to see that. And we thought, all right, he's a physicist, isn't he? Okay, that's what he was looking forward to. Not enjoying a new culture, but watching the toilet flow backwards. Okay, never mind. That was the Coriolis effect. Because that was south of the equator, the spin of the Earth has the opposite effect down there. Okay, spinning the same direction, but it has the opposite effect. Now, an anticyclone is a high pressure area. We usually don't call it that, but that's what it's called. The air is synced, warmed, and the relative humidity is lowered. So you typically don't have rainfall in a high pressure zone. And I can remember some summers we've had here in the southeast when we had what they call a Bermuda high sitting off to the east of Florida, and it just sucked in warm, dry air all the time, and it would just sit there, and we never got any rainfall, and we'd have so droughty conditions back then. Hated Bermuda highs. Okay. Now, why they put this in now, but it's in your book. This shows, is that someone else coming in? I don't think so, but let me check. No. Okay. This shows what they call, some places would call it the tornado tracks. The tracks that the cyclones usually flow. And you find they usually move west to easterly. Okay. Now we're going to talk about that a little bit later, but most of our prevailing weather comes from west to east. We look to the west of us to see what's happening, say in Louisiana, Texas, Mississippi, to see what we're going to get next. And if you think about it, most of the storms track this way. They'll hit Mississippi first and then come into Alabama. Later move to Georgia. That's why I said we're supposed to have a lot of rain on Thursday. I'll be teaching here. We hope to get behind it and follow it into Georgia. It's supposed to be rainy there on Friday. We hope that it's out of there by the time we get over here to the farm in south central Georgia. Okay, eastern Georgia too. Okay, those are the tracks. And if any of you were around, I bet you were, I don't know how old you were, back in 2011 when we had those severe tornadoes, they followed this track almost to a T. The thing is, it wasn't a narrow track, it was all up and down the coast. I remember seeing on the weather map, they said, okay, there's 4 or 5 category 4 tornadoes or higher out there. We're only going to focus on the ones closest to us. That never was said before. You know, if there was anything, they were all over it. They were only going to focus on the ones closest to us because they could not track all of them. It was an awful, awful day. The next time we went to the weather center after that, they had a nice video they showed us of, and Jerry explained to us, is this one sort of informal scale that the meteorologists use a lot. They combine several different data points, and he said the number, he had not seen a number, I can't remember what it was, higher than about 400 to 500, maybe 600. That day it was 900 or something. Unprecedented, the level of instability in the air. They said everything was set up perfectly for the worst possible weather we could get, and boy did we get it. Okay, so those are your typical storm tracks. In the old days, these were the major ones. The ones through Oklahoma came up here, the ones through Kansas, those and that one. Those were the famous ones. That's where tornadoes usually went. And what made them so bad is there's no trees out here to block them, so once they hit, they just can tear up so much. No mountains, no trees. Here we get lots of trees and lots of change of topography, so it tends to break them up a little bit. But boy, that day nothing was breaking any of those up. So it seems like now we have become, more tornadoes are coming in this way. They still get plenty that way, but we're getting more and more this way. There were some major ones in Dallas in past years, and we've probably been on track for some of those too. Okay, enough said there. Got to click the screen. Okay, now we're moving into major storms. Okay, waves and cyclones typically, those can be major storms. What a major storm is defined to be is rapid, violent weather changes. Okay, rapid, it happens in a short period of time. Violent is major, and you have changes, either hot to cold, cold to hot, something like that. Most of the time, warm to cold. That's the most violent. Often associated with a frontal passage. Different air masses, warm, moist, cold, dry, colliding. That's when the rapid, violent weather changes occur. Okay? Now, three major types here, and we'll hit them in this order. Thunderstorms, those can be severe, and you have thunderstorm warnings. Tornadoes can be incredibly severe. Hurricanes, even though they're not as intense as tornadoes, they cover a much bigger area. So they can do the most damage. Not the most damage to a particular area, but the most damage overall. So let's hit them in order. First, the thunderstorms. Usually develop in warm, very moist, unstable air. This warm, moist air packet is being lifted, sucking in the cold underneath. That lifting creates the Coriolis effect. As it goes up, you can form this. Here are the three stages they name. The first of these is the cumulus stage. Here is that air being pulled under low pressure, so it's sucking air from around it. Remember, this is warm, moist air too, being sucked up high where it cools off. Okay, that's what forms the instability. Now, the first, the cumulus stage, is just when it's being formed, pulling it up. You're forming those big, tall, monstrous cumulus clouds, but nothing happening in it yet. When it gets mature, this updraft, warm, moist air, is being sucked upward. As it's sucked upward, it's cooling around these ice crystals, because look at this. This is 8 kilometers, 9 kilometers high. That would be 4.5, 5 miles high. It's cold up there, folks. It's really cold. You get the ice crystals in there, and you start forming, the water starts condensing on the ice crystals. Okay? You're going to have some rain there. Now, at the mature stage, the updraft that was coming in here no longer supported. Okay, support those growing ice crystals. They go even further up. They get so heavy they start falling. So now we have warm, moist air going up, cold air moving down. That creates the circular pattern here, the counterclockwise flow of air in this northern hemisphere, and this is where your rain starts. Now, if you're lucky, it all falls as rain because it heats up and melts as it comes down. If you're not so lucky, some of that ice that was formed here, it may have been carried up and down several times, growing those ice crystals bigger and bigger and bigger until finally they fall, and don't fall as water. They don't melt enough. They fall as hail. That can cause some damage. Those are severe thunderstorms then. Hail formed in the accumulation process, formed through the ice accumulation process, and makes its way to the ground. The final stages, all the updrafts are exhausted, and all you have now is rainfall. And it can still be fairly severe, but usually it's just heavy rain, maybe not as much lightning as thunder, though you still could have some. Okay? But you're on the downward path yet. You've covered most of it. I'm getting hard to breathe again. All right. Hold on just a minute before we hit this. Sorry. Now, lightning and thunder, they go together. Number one, you can't, anytime you have lightning, there's going to be thunder. Now, it might be that the lightning's so far away, you'll never hear the thunder, but that doesn't mean there wasn't thunder produced. It's just you may be too far away to hear it, because light travels a lot further than sound does. Sometimes, though, you hear thunder and don't see any lightning. Well, that promise you this, you don't have thunder unless there was lightning somewhere. They go hand in hand. If you have one, the other was there somewhere. Okay? I think someone else left the class because it dropped to 13 students plus me. So hopefully they'll be back. Okay, what's happening here, the updrafts going into those clouds like we saw last time, the downdrafts are happening because the ice crystals are getting so heavy they're coming down, and you got circulation precipitation. What's happening there, you got lots of movement. And anytime you have movement, you're knocking off electrons. Some places the electrons may be accumulating, some places they may have a deficit, but you're changing the electrical nature of the clouds. Okay? Now, where you have excess electrons or a deficit of electrons, you have what they call a potential difference. Okay? Now, the charges accumulate in different parts of the thunderhead. This part could be positive, this negative, or vice versa. Doesn't matter. There's a difference there. Okay? And anytime you have a large enough potential difference between the negative charges and the lack of negative charges, called the positive charges, you're going at some point to discharge. That's what lightning is. It's the discharge between the charge centers. Okay? Now, they haven't mentioned where those charge centers are. It can be from one cloud to the ground. It can be the ground to a cloud. Believe it or not, you can have lightning go from ground to cloud or cloud to cloud. Okay? What it takes is a big enough potential difference. Now, here's what the from and to is about. If the charge center up here in the clouds, let's start with the first one they say, cloud to ground. The charge center up here in the clouds is excess negative charge, which means these negative charges repel negative charges in the ground, so they go deeper in the ground, meaning the positive charges are sucked up here. Once that potential gets large enough, it goes from negative to positive because the electrons are negative. Okay? On the other hand, if you had your positive up here in the clouds, and that's going to pull the negatives toward it, push the positives away from it, when that potential difference gets great enough, it goes from ground to cloud. And I've seen in some places, not in this book, but I've seen pictures when the photographer happened to catch it right at the right time, and you can see the lightning is going from the cloud, from the ground to the cloud. Incredible. Guess what? It'll kill you either way. Same huge amount of potential difference. It can shock you to death. Or one charge center is negative, positive, they go this way, positive, negative, go this way. It doesn't matter, cloud to cloud. Okay, that's what we'll see quite often. You will see it go cloud to ground, and sometimes it happens so fast, you may see it go ground to cloud, you don't know it, it hits. Okay, now, what lightning is a rapid discharge of electrical energy. That's what it's talking about here. Wherever that happens, that is heating up that one little space that it's going through incredibly hot, which forms a compression wave around it. And then as soon as that passes, you have a collapsing of that, which is another pressure wave. So the expanding pressure wave from the heated air, oh, here comes Angelita back. I didn't know she had left. That must have been one. I'm transferring from my phone to my laptop. Oh, okay. Glad you're here then. Okay. So that's what creates the thunder. The expanding pressure wave. Now it keeps popping up and down. Let's see if anyone else is trying to get in. Don't see anybody. Okay. that expanding pressure wave and then the collapsing, that's what creates the thunder. That creates a very big sound wave, pressure wave, and that's thunder. Anytime you have lightning, thunder is produced. Anytime you hear thunder, lightning had to have caused that thunder. So they always go. Even though you won't always hear the thunder when you see lightning, or you won't always see the lightning when you hear thunder, it's still, you know. And as they say, if you can hear it, you're susceptible to getting hit. If you can hear the thunder, you could get hit by lightning, because they always go together. I'm trying to get the picture to come up. There it is. And this shows this. When you have the negative center down here and the ground becomes positive, you could have cloud to ground lightning. When you have the negative center here, now don't worry about the rain, they just drew that in. The positive center here, the negative down here, you have ground to cloud lightning. Or a negative center here, positive center there, cloud to cloud. Or even within one thunderstorm, one cumulus cloud, you could have cloud to cloud, a negative center here, positive center there. You could have cloud to cloud here. So it doesn't have to be two separate clouds. It could be within one cloud. Whenever you have lightning, you do have thunder. Whenever you hear thunder, there had to be lightning somewhere. Okay. The second of these major storms are tornadic storms, and this begins on page 585. Now you'll see here on that page, before we get to it, a picture of a hailstone I just as soon never see. Look at the size of that thing. That could create a huge dent in your car, could break the windshield, could break glass on your window in your house, and it can certainly cause roof and crop damage, all kinds of damage, car damage, whatever. So they showed the picture there. I would have put it on the earlier page. But what is a tornado? Now, a tornado is the smallest, but the most violent of these weather disturbances. A thunderstorm can cover a fairly large area, or tornado typically is pretty small, pretty compact, but it's incredibly violent. Rapidly rotating column of air, they're always spinning. The diameter can be between 100 and 400 meters. Now, I don't know if you think in terms of meters. 100 meters is basically from the goal line on one end of a field to the back of the end zone of the other end of the field. Now, that's a pretty wide diameter, okay? But that's just 100. That's the small one. The 400 meter, that's close to a mile, okay? Close to a mile wide. And some of those, that one that went through Tuscaloosa back in 2011, that was close to a mile wide. The one that hit, what was that city, Hacklesburg or something like that, up in northwestern Alabama? I mean, that was a monster of a storm. It had to have been close, maybe even more than a mile wide. It was just incredible, the amount of energy being released that day. Wind speeds up to 480 kilometers per hour. Okay, just to get an idea, that's approaching, not quite there, but approaching 300 miles an hour. I'd say 250 miles an hour. That's incredible wind. Okay. The damage produced mostly by the high winds, but also by the drop in pressure at the center. So it's lifting things off the ground, spinning them around, and that's what gives it the dark appearance. Let's see if we have a picture. Yes, there it is. That's what gives it the dark appearance here. That's because it's sucking up soil, dirt, sand, paper, trash, anything. That's what makes it look dark here, because that low pressure is sucking it off the ground, and the spinning is making it go. Coriolis effect. And it's an incredibly intense pressure difference, incredibly high-speed wind. Okay. So most of the damage caused by wind. The wind is caused by the drop in pressure and the flying debris that's carried by that wind. I don't know if you saw the movie Twister. This was an old movie for y'all. It was new for me. I never saw it, but I remember seeing the advertisements for it, and they actually showed cows flying through the air. I guess that may have happened before, but I think that was a bit of a stretch. But I do know my wife grew up and went to school in Huntsville, Alabama, and they had a tornado that went through not that awfully far from where they lived, and literally cars were picked up off the ground and thrown around. I don't think they got way high in the air, but they were lifted and hit other cars and hit houses and things like this. Um, so flying debris, that's the most dangerous part. These are associated with intense thunderstorms. Where you have a line of thunderstorms, you could have tornadoes forming in those. Okay. Now, they just went right into hurricanes, didn't they? In the book, on page 586, they have this blurb here on, they call it concepts applied. These are the levels of tornado and tornado damage. Now, I think they may have changed the scale slightly, but I think these are called the EFs. EF0, EF1, 2, 3, 4, and 5. 5 being the heaviest. And I think those that hit, I think at least 4 or 5 EF5s or very strong 4s, I know went through Alabama that day, and probably more than that. Okay? I mean, it was incredible. That was April something, 2011. I don't remember exactly the date. 27th? You sound like you were there.
Yeah, my house was completely destroyed.
Oh no. Where were you?
I was in it. I was in the basement.
Oh man. I bet you that was frightening to come up and look at it, wasn't it?
Let's put it this way. If I would have slept 5 minutes longer, I wouldn't be here.
Yuck. I'm glad. Did someone wake you up or did the storm wake you up?
Yeah. My mom woke me up. I actually was in finals week.
Yeah.
Left and
Oh
my
wow.
first time through.
Uh-huh.
And yeah.
Wow. Yeah, they are some mean things, and that um, I was safely watching it on TV, but none of them came super close to us. But boy, where were you living at the time?
Pleasant Grove.
Oh yeah, Pleasant Grove got hammered really badly, as many other communities did too. One of our registrar, I think, was living in Pleasant Grove, and she sustained minor damage at her house, but it was way more than she ever wanted to have. So, yeah, it was awful. Yeah, so when we're talking about that, and that I think probably was an EF4 or 5. Did you ever hear the classification?
It was a 5.
It was a 5. Okay, amazing.
And when it came through, it was so freaking huge.
Yeah,
And there was other tornadoes actually spinning off of it.
yeah, yeah.
It's crazy.
It's absolutely incredible. And that happens with hurricanes. They spin tornadoes off of them. Tornadoes spin little tornadoes off of them. And thunderstorms, that's what they were talking about before, spin tornadoes off of them. The EF5, just to get a perspective, the winds can be from 261 miles per hour up to 318 miles per hour. Homes, like it said here, demolished and swept away. That sounds like what happened to yours. Automobile-sized missiles fly through the air more than 100 yards. Okay? The bark is actually taken off trees. Now, I've never been super close to any of those, certainly not as close as you were, but we've had some minor tornadoes happen at the farm in Georgia. And I remember one person describing they saw this pine needle sticking into a telephone pole. That wind had been that strong, it drove the pine needle into the pole. Until somebody, and this was not an EF5, it was nowhere close to it, until someone realized no, it had driven it through the pole and it was on its way out before it ran out of energy. And I went, oh no, I don't want to be around that. Okay, not at all. Uh, and so if you have your book, go through that table of tornado damage. Okay, the reason I'm postponing a little bit now, they're going to show it for hurricanes and then I'm going to compare it to tornadoes. Okay, now hurricanes, I've already sort of talked about this. They start off as tropical depressions. What that means is a low pressure area. In fact, they'll sometimes call it that, a tropical low. Area of low pressure, usually down in the tropics somewhere. And that tropic could be the Gulf of Mexico. Most of the time we think of the ones coming from Africa, but some of these this year have started in the Gulf of Mexico. Some of them moved into the Gulf of Mexico, but some have actually started there. That's enough of a tropical area. Start as a low depression, low pressure area, tropical depression. The winds are generally more than 55 kilometers per hour or less, and that would be, I would say, 35 to 40 miles per hour. I'm just a close guess. That's still going pretty fast, okay, if you get hit by that. If they continue to strengthen, then the more intense low pressure, what's happening? The low pressure becomes a lower pressure. And the lower the pressure, the more the wind is sucked up, the higher the wind speed become, and it goes from 56 to 120 kilometers per hour, and that would be about 72 miles per hour. I think they usually count at 75. So somewhere around 35 to 75 miles per hour. Okay? And then if it continues to grow in strength, which usually means more heat, more energy, lower pressure, higher winds, very intense low pressure area, and they usually will measure these by the barometric pressure at the center. That's what they use to measure them by and say what kind they are. The winds are in excess of that 120 kilometers per hour. That means more than 75 miles an hour. Now that's a hurricane, okay? These would then be a hurricane. Fully developed hurricane has a very, and this is so strange about a hurricane. The eye, the center of that hurricane, is incredibly calm, okay? Surrounded by a wall of incredibly rapid moving air, but perfectly calm in the center. And I think, whoa, here's Andrew. He must have had to go out and come back in or change the device or something. I hope he's the only one. Let's see if anyone else was doing it at the same time. Oh, yeah, I got him. Okay. All right. Now, I don't think I can get it to advance. Okay. Here is one of those hurricanes. I don't remember which one this is. I thought at one time it might have been Andrew, but it seems like it was a different one. But here is the eye of the storm. You've heard of that phrase before if you ever watched Rocky. No, never mind. In there is perfectly calm. The wall of the storm, which would be in here, that's the most violent, intense winds you'll find outside of a tornado. Okay, the eye is perfectly calm, but outside the eye, incredibly rapidly moving winds. It's just has to be incredible. I had a friend when I was in grad school at University of Georgia. He was an undergrad. He was actually a forestry major because he liked being outside and he thought he might like to major in forestry. But then once he graduated, he decided, no, I really want to fly. His dad was a pilot for one of the airlines and he wanted to be a pilot too. So he went to pilots. Of course, he already, I guess, knew how to fly. His dad had taught him, and he went through, got all his credentialing. But that was back at a time when we were going through a sort of an economic depression time. The airlines were hurting like crazy. They were being bought up, merged, shut down, various things. His dad, in fact, lost a job at Eastern and was picked up at Delta, so he became a pilot with Delta. Eastern doesn't exist anymore. And that was about the time Doug was reaching the point of trying to become, get employed as a pilot. Well, none of the airlines, major airlines, were hiring because they were laying off their experienced pilot. They didn't want a rookie coming in. So what he did, he was able to get on as a pilot for NOAA. Anyone know what NOAA stands for? National Oceanic and Atmospheric Administration. NOAA. Not NOAH, but NOAA. NOAA. And he was a hurricane jumper, basically. What he would do, had a big, probably about like a commercial airplane, I'm guessing a 737 or something about like that, that they would take up, and it was fully equipped with equipment, with meteorological equipment, and they would take it and fly up over the storm, and that had to be the roughest part, and then they would go down into the eye and fly around in the eye, and all the technicians that were on board were then collecting data all the time, and that's where they got the barometric pressures at the center of the storm. And that's how they classified the tornadoes. And then either when they had gotten everything they could get, or they were running low of fuel or whatever, then they had to fly out, cross over the storm, and head back to home. That's what he did in his first, I guess, several years as a pilot. Later got hired on at Delta, and he was a Delta pilot from then on. He's already retired, by the way. So anyway, he was a hurricane pilot. Okay. So he flew down into that calm eye, but totally surrounded by intense weather. Okay. I think someone has a phone on, by the way. Okay. Here is a cutaway view of what that hurricane looks like. Now this is just representative. The distance in here can be up to 40 kilometers wide, okay, in the eye. That's pretty wide. 40 kilometers would be about 24 miles in the eye. Okay, now that's a bit strong. Probably the eye is a little less than that, okay? And that's such low pressure, it's sucking air down into it, and the air is sucking in so fast, the Coriolis effect again, making it spin, and it spins in a counterclockwise direction because it's a low pressure area, and that's sucking air then up into the clouds, and that's usually warm, moist air because they gain strength over the oceans. In the summertime, the hot part when they get the most energy in the ocean, it's sucking them up. All that moisture is going in here, swirling around, and that hauls off, and you have intense rainfall right under those. Okay, and for bands going out. In fact, the rainfall is going miles and miles out. Here's Kendra. Must have had to go out and come back in. These can be really wide. I mean, incredibly wide. Let's see what their scale was here. I can't. Every time that pops up, I have to click again. Going out to the thunderstorms go out, it looks like to 40 to 40, that's 80 miles. That would be about, 80 kilometers, about 48 miles that you have really intense weather. And then the bands around there could go out as far as, looks like, close to 100 kilometers in either direction. That's 200 around here. And that would be neighborhood of 120 miles that you could be affected by that rain. So that could be as much as 120 miles here that still being affected by really intense weather. Pretty amazing. Now, I happened to be in a book study with Jerry Tracy at our church, I only went one time. I don't know if he continued or not. But someone, we were studying a book, I can't remember its name now. It's a really good book. But someone was just commenting, it had nothing to do with the book, of why in the world terrible things like hurricanes happen. There's just, the woman was saying, I just can't believe that a loving God could, have those being produced. And Jerry said, well, wait a minute, wait a minute here. If it weren't for hurricanes, we would not have life on this planet, or it would be a very miserable life, because all the heat would be concentrated at the equatorial regions, and the polar regions would be so cold that nothing could live up there. It would be miserable living in here, and in between you would have just incredible changes of temperature. He said if it weren't for hurricanes to distribute the energy and the heat from the tropical regions to the temperate and ultimately onto the polar regions, he said we wouldn't exist as a planet. We couldn't exist. So it's all part of a better plan, believe it or not. Okay. Uh, let's see. All right. Um, it looks like to me. Oh, here's what I was going to show. I thought they were going to show it here. They didn't on the slide set. Here is a table for hurricane damage. Now, it's not just talking about damage. These are the classifications for hurricane, 1 through 5. And if you've got your book, we don't have time to do it now, but if you've got your book, take a look and compare these. The most powerful hurricane, the winds are up to 155 miles per hour. In your tornado activity, and these are right across the page from each other, um, that would be um, that's a category 5 hurricane. That would be in a category 3 tornado. Okay, so the tornadoes go much stronger, 318 miles per hour as opposed to 155 miles per hour. So basically twice as much wind speed. Okay, somebody's microphone's on. Okay, uh, all right. I think we're going to have to stop there, and we'll hit weather forecasting next time. Okay, and then we'll get into climate. I sort of hoped to get the climate today, but we didn't. Then we'll talk about climate. And even if we don't finish the chapter on Thursday, we'll have plenty of time on Tuesday to wrap it up. Okay, so it looks like today we'll stop here, and we'll start on the last chapter lab, topographic maps, next. And then on Thursday, we'll continue and probably finish chapter 23. When we finish 23, we'll probably do like we did last Thursday and have a time when people can kind of catch up and see if you can have any questions or other things. Give you some extra time to get your labs and your tests done and completed. I don't know how much extra time we'll have because we still have a bit to do in 23, but I think we won't have to take the full 4.5 hours. I think we'll probably be able to finish in maybe uh, 3 to 4 hours, I think, probably. All right, any questions before we shut it down? Okay, now when I say shut it down, that means I'm just stopping the PowerPoint here. Okay, so I'm going to turn off the PowerPoint here, and you want to take a little break before we get started. Okay, anybody? Say again?
Yes, sir.
Okay, so let's try to keep it less than 5 minutes. I'll pause the recording here, and then we'll pick back up and get started on the lab. So take your quick break. Try to keep it 5 minutes or less. I've got to run downstairs and take care of a couple things, and I'll be back with you hopefully within 5 minutes. Okay? Okay. I'm going to my, well, I thought I had whatever you call it, Blackboard open, but I don't yet. So let me get Blackboard open. Okay, Drew, your microphone's on. Boy, was it all this bad while I was gone? I'm sorry. I guess I missed the worst of it. I hope. Hope it gets better. Okay. Um, all right. I'm almost there, but not quite. Okay. Your microphone's on. Okay. Um, what I think I'm going to do is get back to the meeting here. Okay, I'm going to share my screen and show you how I'm going to get there. Okay. Um, I am. Okay. Let me see if I can. Yeah, there's a button. Yeah, I muted him. Okay. Y'all can't hear him anymore, can you? Okay. I wonder if he can unmute himself, though. He can he? Oh, okay, good. Okay, so I don't have to unmute him. So I'm sorry, I should have done that earlier. Okay. What's that? Okay. Okay. I was just checking to make sure nobody was out there waiting while I was not here, so I'll get that down. Now this, you can't see it, but this taskbar is in my way of seeing things, and I might have to move y'all around a little bit. I got about 4 people over here on the side, and I think I'm okay for now. Okay. Now I'm in physical science, but this is the wrong physical science. Um, so let me get out of this one. I don't know how that one came up. I was on the right one down here. Physical Science 111. This is our class. You can see this on my PowerPoint, right? I mean on my Zoom, right? My Blackboard. Can y'all see this? Okay. So I'm going to click on that, go into the class. Now, we got a few places to go. There was the announcement. I'm going to turn that off for now. So here's where we're heading. Under weekly assignment, but I can't get there because Angelita's in the way, so I'm going to move you up here, Angelita. No, a bunch of you. Okay, let's go to weekly assignment. Okay, and we're in week 6, believe it or not. That means we've got next week, and that's our final week. So we're on the short rows now, folks. Okay. Instructional materials, lessons, PowerPoint, blah, blah, blah. So that's where I click, instructional materials, under week 6. And then here are the 2 labs. One's a PDF file and one's a doc file. I'm going to open both of them, but we're going to look at the PDF first. So here, whoops, you can't click on it because it doesn't underline. You have to go to the 3 dash. They call these ellipticals. I don't know why they get that name. Those 3 dots, click on download. Well, you see it. Okay, now it's downloaded. Lower left corner, click on that, and here comes the thing. So we'll get there in a minute. Let's go back and let me, oh, yeah, you can still see that. I need to go back and click on the other one, and I'll probably lose you for a moment here. Say that again. Yeah, yeah. I'll try to explain how they tie together in a minute. Sure. However you want to turn it in, y'all have been really good about that. For some reason, I can't see the second one now, so I'm going to have to go back. There it is. No, it isn't. It always does this to me. It blanks out the one I'm looking for. So hold on a moment. I'm going to get out of this and go back to, oh, I know what part of my problem is. Angelita, you're in the way. Okay, here we go. I'm going to minimize this one so I can see the other one. Okay, I know I've lost you for a bit, but I'm coming back. I promise. Let me go back here. There we go. Here's the doc file. Oops, I can't click there. I got to click here. Now, I'm not going to be able to go back and forth between these as easily as you can because I'm projecting everything. So if some of you have these printed off already, then it might be helpful. There's the one we'll do second, okay? And you notice it has a link here. We're going to go to that link later, but we'll go hit first the first one if it'll have it up there now. I think that's that one. They black out what's on it. So let's see, is this one here? This drives me nuts. I don't see this one. I had it open. Oh wait. I had the PDF open and now the PDF icon is even showing up down here. So do I have to open this again? I never closed it. Okay, we'll start here and worry about the other one later. So this is where the lab begins, topographic maps. Okay, now a map. What's a map? We are recording, good. It shows a convenient representation of an area, describes basic features and locations. Now, it depends on what kind of map you have. A road map, of course, is going to show roads, of course. That's why they call it a road map. It's going to show political boundaries, states, counties, cities, whatever. Okay? Some natural features like rivers and lakes, because those roads are crossing rivers and lakes and stuff like this, and you want to know where you are, not be surprised. A topographic map is a different kind of map, however. It shows topography. Now here's the tough thing. A map is a two-dimensional thing. You have a flat piece of paper, right? But this is trying to show you a three-dimensional shape of a surface, including mountains, hills, valleys, and that kind of things. It will show some roads. It will show some buildings, maybe some dams, political boundaries. It may show any of this stuff, but its major features are the topography, the three-dimensional area. And the other things are there to show you the relationship between them. Okay? Now, we're going to be using the latitudes, the parallels, north-south lines, longitude, and meridians. We talked about that in the last lab. Okay? But these are going to focus on the contour lines. Now, what's a contour lines? That shows an area of equal elevation. All right. Now here is sort of a picture of a landscape, kinda. Here's a lake or ocean or something here. You know that everything right here on the shore is at the same elevation. It actually looks like there might be a road along there too, and that's all at some low elevation. This obviously is a higher elevation. This is a higher elevation. You have some higher elevations back here. Here this goes up really abruptly. Here it goes up really gradually. Here you have a valley in between the two high elevations. So what does this look like on the topographic map? Well, here's a topographic map of that very area here, or at least part of it. Here is the seashore right here. This would be the seashore right here, somewhere right here. It's not real clear, but there's 20-foot elevation. That must be as high as that seashore goes. Okay. Now, this is not showing up well here. I don't know if when you printed it, it shows any better, but the shoreline is a 0-foot contour. So this is the shoreline here. Okay, I don't know what this 20 is here. I guess this is a 0 here. So you must have this coming down here in between. Again, it's not showing up super well. But notice here where it's so steep going up, these are your contour lines. Now this one doesn't show the scale, but you can tell here the smallest you see is a 20 foot. That's your contour interval, 20 feet. Okay, so this is 0, 20, 40, 60, 80, 100. Well, I counted them wrong. This is 200 here. This is 0 here. There must be 10 lines in between there. I just can't see them. The highest point here, that would be that point right there, is at 275 feet. 260 is back here. This one over here doesn't get as tall. It only goes up to 260. Okay, so this one's a little taller here, but it must be setting further back. Here's your 200 foot. There's your 100 foot. Here you can tell better. It's hard to tell for sure though. 20, this is 100. 120, 40, 60, 80, 200. Okay. And again, where the lines are closer together, it's steeper. When they're further apart, it's flatter. Okay. And sure enough, that's what you see here. That's what a contour map shows. It's a two-dimensional map, but it gives you three-dimensional concept by those contour lines. Contour lines are isoclines. Lines of equal elevation. That's exactly what they are. So let's scroll down some further here. Okay. Now, unfortunately, this did not print off very well, did it? The following characteristics of contour lines, most of which are illustrated in that figure we were seeing, govern the construction and reading of these contour maps. Now, these are well worth your read. The reason is, the first, I think, 5 questions or 4 questions are going to be based on these statements here. And some on the first page, but mostly on these. Read these. They're worth it. Now, if any of you can't read some of the words, ask me. I'll help you make them out. The materials, we're not going to use soft clay. We don't have that kind of stuff to deal with. We can't be hands-on. So, but these are worth your read. You're going to be answering some questions on those shortly. Okay? Procedure, we're not doing any of that, so don't worry at that. Now, this one came out clear as a bell. Why the middle one didn't, I don't know. Don't worry about any of that procedure. But, starting with results here, what do topographic maps show? First page, second page. That's where you'll get it. I think that's pages 345 and 346, I think. Okay. What is the relationship between the closest of the contour lines and the steepness of the slope? You can find that on that previous page, 346, I believe it is. Also in that reading, you'll find the answer to this one. What happens to contour lines across a valley? Go back and read that page. I know it was sort of fuzzy, but you can make it out, I think. And how would a nearly vertical cliff be represented on a contour line? Well, a nearly vertical cliff would be steepness, really steep. What would that look like on your contour map? Now, you might want to wait till you're finished with the whole lab to answer question 5. That's only 5 points worth. We got to do better than that, folks. Well, here's where we go next. Invitation to inquiry. Okay? Now, I don't think this website is active anymore. At least it wasn't earlier. But what you can do is Google, however you want to do it, search engine, look for Devil's Tower National Monument, Wyoming. And if you can connect something else with that, You can call it relief map or contour map. That's what you want. Find that on your device. Okay, I don't think this is active anymore, but if it's not, you can still find it somewhere. Devil's Tower National Monument, Wyoming. You may or may not put it there. Make sure it's in Wyoming. Either relief map or contour map. Okay, and then you can answer these questions. Now, I want to point two of them in particular out to you. And what we're going to do next, you'll see some of these same things here. First, it says, what's the elevation of Devil's Tower? Okay, that means the greatest height of it, right? It'll also say, what is the contour interval of the map? The one we were looking at earlier was 20 feet. That's the between two contour lines is 20 feet. I don't know what it'll be on the one you're looking at. Find that. It's usually going to be a legend at the bottom, and when we move to the next part, you'll see where that's approximately where that's located. But then number 3, what's the approximate height of Devil's Tower? Is that not the same as elevation of Devil's Tower? What you think? Is that asking the same thing? Okay, no, you're close, but not quite there, but I think you're on the right track. The height is the difference between the base that you were just talking about and the highest point. That's the height of the Devil's Tower. How much does it rise above its base? However, the elevation is how far it is above sea level. Well, if this is in Wyoming, sea level is way, way down there somewhere. So the elevation is how high it is above sea levels. The height is how high it is above its base. So you read the contour near the base, read the contour at the top, take the difference of those. That's the height. Is that okay? Does that make sense? Anybody? Okay. The next question is sort of nebulous sound. Anyone got a question on it? Okay, the next question is a little nebulous. What is the top of Devil's Tower like? And I think what they mean by that, what's it like on a contour? Like if you see a contour line out here and no more up here, and it's a 20-foot contour, then it's relatively flat. Probably a little bit domed or something like that. And if you have a contour line here and then maybe another one here and here, then it's sort of sharply domed. Okay, that's what it's talking about. What's the top of it like? But if the site you go to, it gives you more detail than that, you can write that down too. Then the next one is Devil's Tower too steep to hike to the top. Now, I'll let you decide on that one. To me, a hike is a fairly easy thing you're doing. I'm not talking about scaling it, mountain climbing it. I'm talking about hiking it. I'll let you determine that, probably what you read. Well, there's 5 more questions. That gets us up to 10. But guess what? That's not 25. Okay? And that's all for the lab on the PDF. So now let's go back to the, there it is. Okay. Let's go back to the PowerPoint. Not the PowerPoint, the Word document. Okay. And let's do a screen share of that one. There it is. So here's where we pick up the next part. Okay? Now, what you have to do is go to a website. Now, I haven't checked it out today, but this one I think is active. Okay? So let's make sure it is. I'm going to take this. I'm going to see if I can just click on it and go to it. Let's see if I can. No, I can't. So I'm going to have to copy this to my, so I might have to enable editing here. Okay. Yuck. Okay. Let me go back. I don't know why that shut down. Now, No. The PDF was the one we were looking at. This is the doc file.
No, I got
Okay, you're talking about the,
Word documents different. There's two folders.
yeah,
So James, you was able to pull the doc and get this lab?
Yeah, I clicked on week 7, and then I clicked on.
okay. I'm going to try to get this back up so you can see it. Okay,
He's got a tab. He's got a tab under week 7 called Lab 7, and both files are there.
yeah. Okay, where we are, no, we're week 6, not week 7.
Oh, sorry.
Yeah.
It was week 6. So I said the wrong one.
Okay, it's lab 7, week 6. Okay, we did 2 and 1, or sometimes stretched over. Can you see my file here? This is under instructional materials. It's the physical science thing in Blackboard. Then you go under week 6, and then you look for instructional materials. Click on that, and the one we were looking at was the PDF file. This is the doc file. There are 2 different files there.
Okay, something must be going on my end because when I downloaded the doc file, it gave me the PDF. So I'm going to try to re-download it, I guess.
Yeah. Hit the 3 dots that are next to the doc file. Be sure you get across there and click on those, and that's the one you open. Yeah, one's a PowerPoint and one's one's a Word file and one's a PDF. Okay, so let's see if we can go back to, where were we? Okay, I think I copied the other one. So since, okay, let me get back to this one. Okay, so I'll make sure this one's up here. Okay, now what I'm going to do is take this. I think I did it already, but I'm going to do it again. I thought I could just click on it, but that didn't seem to work. Okay, I'm going to, oh, control click to follow the link. Let me try that. Control click. Okay, that's taking me there.
So this is a 25-point lab, and it's 20 on the doc, on the Word document?
No, okay, we were 10 on the other. 5 at the beginning, those 5 questions, then 5 on Devil's Tower, and now the rest of them are going to be here. Now we're going to exceed 25 points, but I'll work it out so you get more partial credit and stuff like this. This is a geologic mapping. Now you can't see it yet. Let me see if I can get this up on the share. There it is. Okay. Can y'all see that now? Okay. This is from that. You can do a control click on that thing in the Word file and you get right to here. Now this first page is really pretty. Okay. I'll just give you a little bit of an idea. This is not a topographic map here. It has some features on it. This shows a river valley here. I can't think what river that is that dumps into the Mobile Bay, but it's a confluence of several rivers. This is the Black Warrior over here, and this I think is the Cahaba coming from here, and maybe the Coosa's coming in here too, but they're all getting together here and coming in, or maybe the Cahaba comes down here, I don't know. But anyway, this is very much a coastal area. This is above sort of the Florida Panhandle. That's down here, so you get a little bit, I think they may call this wiregrass or something else. You got a little bit other, these are geologic maps, okay? Not going to go a great detail into here, but these are riverbeds, basically, you know, that cut up through here. We are here. There's Jefferson County. We're in a different area, and you see the lower part of the Appalachians are coming down here.
Did you hit the record button?
I hope so. Let me see. I'm pretty sure I did. Yes, we're recording. Okay. Yeah, I think I did shortly when I came back. Maybe after I muted, no, right before I muted him. Um, so let me minimize that again. Okay, so this is just sort of interesting. But on your, okay, I'm going to be going back and forth now. I hope this doesn't get too confusing. Go back to the doc file. We got into the map, and here's what it says to do. Go to the map. We got there. Scroll down to the listing of the geologic maps until you see Bessemer. Go to the fourth column where you see QS20 Plate 1 PDF. Click on that, and also click on Plate 2 in the next column. And then on Plate 1, move to the lower right corner, expand the scale until you can read the contour lines more easily. That's a lot of blah blah blah. If you can print this off and have this next to you, that would be helpful. And I think I can remember all that. So let's go. We're going to scroll down to see Bessemer, QS20 Plate 1, Plate 2, and then we'll expand the scale on the lower right corner. So let's see if we can do that. Okay, there's the GSA. Oh, okay, here we are back here again. All right, we're going to scroll down. I might have to move y'all out of the way. I think I'm going to, James, you're in the way again. Okay, so let's scroll down here. And we're looking for Bessemer. Oh, there's Bessemer. And there's QS20, right? And we go over here until we see Plate 1. You see that? That's a PDF file. So I'm going to click on that. So now I have another file open, or it's opening now. It takes a while to open. Okay, that's open. While I'm here, if I can remember how to get back to it, is goodness, I got too many things open at once. I seem to have lost the one I need. I'm going to move y'all out of the way again because I found out last time. Okay, I need to go back here and open Plate 2. Now, here was Bessemer. I don't know if you can see this. There's Plate 2. Okay, I'm going to open that one. All right. I'm not going to use Plate 2 for a bit, so let's go back to Plate 1. That's where we were. Okay. Now I think I'm going to have to move you out of the way again. Okay. Now let's go to the bottom right of your scale. No, this is Plate 2. I need Plate 1. What happened to Plate 1? This is what drives me kind of nuts about this. Okay. Gonna have to move y'all out of the way again. Diana, you're in the way. Okay. Go back to Plate 1. I go to the top and do it. Okay. Now, all right. Can y'all see my Plate 1 now? Okay. Now what I'm going to do is go to the lower right corner. Okay. Now y'all are in the way again. Okay, I have to keep moving y'all around. Okay. Okay, here you see. I didn't have to move to the lower right corner of the map, so I sort of did that dumbly. But here is where you go up or down. You see the plus is zoom in, the minus is zoom out. Now, I don't know if you can tell, but there are contour lines there. You see those lines? Those are contour lines. But I sure have a hard time reading them. So what I'm going to do is zoom in until we can read them easily. Okay, that zoomed in some. Okay, now I can see a lot better. You see those lines? But I still can't read the numbers on them very easily. So I'm going to zoom again. Okay, I can see them better now. I can even probably pick out a few of the numbers, but let's zoom in again. If it gets, after a while of zooming in, it gets too fuzzy. Okay, I couldn't tell it did anything. Let me see if, yeah, there we go. Now I'm beginning to see it a little bit better. Yeah, I can almost read the numbers there. See if I can zoom a little bit more. There we go. Okay, I'm beginning to see a little bit. Let's see if I can zoom in a little bit more. I think I can read that one okay, can I? That looks like an 800 there where my cursor is. Is that what you see? Yeah, there's 700. Here's 800. Okay. Now, all right. I think that may be zoomed in enough. So let me scroll down a little bit. Does anyone have the first question on the doc file? On the,
What is the highest elevation you can read on Red Mountain?
okay. So what I'm going to do is, this is Red Mountain. You see it? There's the red part and there's mountain. Okay. It's in red, which is fortunate. Okay. So I'm going to move it up as far as I can and then start moving it this way as far as I can, so I can get as much of it on the screen as I can possibly do. And I think I'm going to move y'all over here. Okay, you couldn't see that, but I could. Okay, so let's go up and down Red Mountain to see what the maximum. Right now I can see 800 right there, and that's not the innermost part. Let's see if we get anything higher than 800. Okay, have we lost some people? Seems like we have. We're down to 11 people. This is not the time to be leaving, is it? I thought for sure they showed some. I'm going to scroll on down a little bit here. Oops, I'm at the bottom. Okay. Now, so let's go to the left a little bit. I'm at the very bottom of what I can see here. Okay. So, what's the highest point we can see here on Red Mountain? They have some things listed, but they don't give any numbers for them. So I see an 800 contour line there. Let's go up and see what else I can see here. Oh, there's a 900. You see that one? There's a 900 there. Let's scoot a little further this way. We may be getting higher. Okay. There I see a 926. Is that what y'all read? Right there, you see where my cursor is? Can you see my cursor? If y'all are on a phone, you might not be able to read it. Well, that looks like a 926 to me, but up here I see a 955. Can y'all read that one? So let's see if I can move any further to the left, because it seems like it's getting a little taller. So there's my 955. There's a 9 something, but I can't read what number that is. Okay, so let's go a little more to the left, right, or somewhere here. East on it. Okay. I'm afraid I've lost my 955. There's a 926. There's a 955. There's a 9 something another. I can't see any more numbers here. If y'all can, point it out to me, okay? Oops, we're at the edge. So let's get up so we can see as much as we can, and then back up. Goodness, right over here. Okay, I don't see any more numbers that beat 955. So y'all want to settle on that one? What was that first question again? Is that what it was? The highest elevation you saw on Red Mountain?
Yes.
Okay.
Elevation you can read on Red Mountain.
Okay. The highest I can read so far is 955. Are y'all in favor of that? Can y'all see where I'm talking about? You might not be able to read it, but can you see?
Location, but I can't read the number.
Okay. Are you reading off a phone or off a computer?
I'm on the laptop, but I'm using two screens. So
Oh, I see.
I actually put the whole screen up, and I still can't see the number. I just can't see it.
Right.
Were you all able to see it, James? Can you see the numbers?
Not really.
Okay. You see where my...
Having to zoom in, and like I've zoomed in so much that it's blurry.
Right. Do you see where my cursor is? Are y'all looking at your own map? Okay, where I'm looking at my map. Okay, you see where my cursor is? There's a water tower, I guess a water tank or something there. Right there at that X is 955. That's the highest I see listed. So let's just call it that to keep from using too much time. Okay, so that answers the first question, 955 feet, because I'm pretty sure this is measured in feet. Okay, and just to get an idea, if y'all are looking at your own map, this is something just south of Winona, a little bit south and west of Winona, a little bit south and east of Winnetka, okay, on the Red Mountain, right next to a thing that says a water tank. It's just, there's a ripple mine, it looks like, or some sort of tipple mine, something like that, is up Red Mountain from there, and just below that is Apple Mine, a little below that on the Red Mountain. Okay, so that's where we're talking about. Okay, so 955, that was the first question. Okay, took us that long to get question one. We could be here a while, folks. Okay, what's the next question?
What is the contour interval of the map?
Okay, now we're going to have to go back south again. So let's head down and see if we can find the contour. See, I was thinking that was my first question, but evidently I didn't write it down first. Let's see if we can find... Oh, can you read that? Anyone got it?
20 feet.
20 feet. The contour interval is 20 feet. Okay, what's the next question?
What is the lowest contour line you can read near the base of Red Mountain?
Near the base of Red Mountain. So let's go back up, at least fairly close to where we were. Let's see if I can find where we were. There's Apple Mine. There's our 955. So let's read the lowest we can find near the base. All right. Now down here I see a 700. I see a 700 there. See a 740. So on the lower side of Red Mountain, I don't know. Maybe a 660 down here. That looks like that could be true. seems like down here you're getting well below the mountain, so you want to just say 700? Let's see on the upper side what we can see. There's a 700 there near the base. And let's see, can we see anything less than 700? Where did I see the 700? I know I saw it, I wasn't imagining it. Okay, there's a 700 there. No, okay, let's go on to the base and let's go down. Remember the interval was 20, so this would be 680, 660. Let's call it 640. Are y'all okay with that? About 640. So there's the lowest one. I can't read a number of it, but I can count the contour lines, and that's why it was important to know the contour interval. So let's say 640. So what's the difference between those two? Oh, that's the next question. I don't know. What is the next question? That then I think is what we're looking for there. What was our max? We wrote 955. 955, and subtract from that, what did I say, 640? And the difference there is 315 feet. And it's not that big of a difference. I mean, it's a fairly short horizontal difference there. Here's the 955 where my cursor is there, and 700 on this side would be down here somewhere. 700 on this side, that's just so much harder to see here, but I was going about to this line here. So that rises pretty quickly up there. So that's 315 feet in a fairly short space. So that looks like a good answer to me. Do y'all see anything you prefer to do better? What's the next question?
List at least one cycling found on this map. Is it cycling?
Say that one more time. One.
List at least one syncline.
Oh, syncline. Syncline. Remember that from an earlier chapter? Okay. I think what we need to do is probably zoom out a little bit. Okay. So I'm going to come to the lower right here and see if I can get my minus here and zoom out, and let's see if we can find a syncline. Is that what you said, or an anticline? Syncline. Okay. Let's scroll out a little bit more. Let's see if we can find a syncline. Okay. I'm getting off scale here, so I'm going to come this way a little bit. Let's see if we can find a syncline. Seems like I found it really easily before. Are y'all looking for me? Ah! I think I see one. Do you see that? Do you see where my cursor is? Anybody? And this isn't the only one, but this is the first one I ran into. What was the syncline? Does anyone remember? It was the trough structure here. And you can tell that by the contour lines. You can see how they bend in here. That forms a trough. Okay? And that's the Kohlberg syncline. Do you see that on the map? Is anyone still with me? Okay. Do you see it? Kohlberg syncline? You see my cursor? There it is, Kohlberg syncline. Now I know kind of where Kohlberg is. I've never been in it, but the new I-22, we used to catch it somewhere off a road that said Kohlberg. Okay, so I know Kohlberg was up there somewhere. It seems like this is fairly close to, oh, maybe, I can't remember now. Finland, it seemed like, I don't know. Anyway, Kohlberg syncline. What's the next question? Is anyone still there?
List at least one fault found on this map.
One fault. Okay, and that doesn't mean it's too fuzzy. That's not the fault we're talking about. Let's see if we can find the fault. I wasn't looking for faults earlier, so I'm going to go back. Well, let's just keep going up. We were going pretty well there, so let's go up and see if we can find a fault. Oops, I'm near the top now, so I think we're off there. Let's go back down and see if we can find the fault. Oh, wait, look at that. You see that one? Anybody? You see where my cursor is? Okay, but you see where my cursor is?
Yes, sir.
That says Opossum Valley Fault. Here's Opossum written down here. Can you see that?
Yes, sir.
Okay, so that's this must be the Opossum Valley, and there's the Opossum Valley Fault right there. Now I want you to pay attention to how they mark it here. A dashed line with the points pointing on this side. That is the Opossum Valley Fault. Do you see how it's a dashed line there, and then the little triangles are pointing to the lower side of it. Okay, there's a fault, Opossum Valley Fault. Okay, what's the next question?
From plate 2, what kind of fault is it?
Okay, now I don't know if you can see my screen well enough, but at the top I have plate 2 open, so I'm going to go up there and click on plate 2. And remember what it was like? There it is right there. You remember that? Dashed lines with the triangles below it? What kind of fault is it? Can you read that? If not, let me see if I can blow it up some. Whoops, I lost it. Isn't that what it looked like? Dashed lines with a triangle below it? What kind was that? Can you read that? Anybody? Thrust fault, exactly. Remember what a thrust fault was? That was a compressive fault, but it had a very low angle thing. The hanging wall was above the footwall. Hanging wall is always above the footwall, but the hanging wall was pressed over the footwall, okay, moving up on it, but at a very low angle. So that was a thrust fault. It says located very approximately sawtooth at the upper plate. Okay, on the upper plate. And that's sort of what that stands for. Okay, good deal. What's the next question?
From plate 1, list at least one anticline.
Okay, let's go back to plate 1. There we are. And let's see if we can find an anticline on here. See, we're doing pretty well going south, so let's see if we can find an anticline. Now, someone remind me what an anticline is. It was an arch-shaped structure, okay? So let's see if we can find an anticline. Something that sort of reads like it, but it's not the same. Okay, I think I'm going to have to go back up again because I'm not seeing one down here. Oh, there we missed one down here. Oh man, y'all can answer several of these. Here was a Muscota Mountain syncline, and there was a Shannon fault. So if you didn't want to put the Opossum Valley fault, there's Shannon fault. But Shannon fault's a different kind of fault. Notice it has a dash line. So it depends on what you want to deal with, but there's another one. Oh, let's keep going. I think we're almost at the edge here. And let me see if I can get those things out of the way. Yeah, there we go. Look at that. Right in the corner. Can you read that? When I get close, those things come in the way. So I can't go close. Right in the lower right corner of the thing. Boy, this is rich down here. I wish we'd have started here. Okay. Dickey Springs anticline. Do you see that? The very lower right corner of the screen, Dickey, D-I-C-K-E-Y, Springs anticline. It must be an arch-shaped structure there. Now that's not the only one on here, but that just happened to be the one I saw first. Okay? And real close to that was the Shannon fault, and we can go and look and see what kind that was. You've already answered the question. You don't have to do it. And then there's a Muscota Mountain syncline. Okay? So there's all sorts of things on here that you could use. Okay. I see another fault hiding over here. Let's see if we can go and find it. Oh, that's the one we looked at before. The Opossum Valley fault over here. It's just another rendition of it. See, it's a thrust fault. This Shannon fault. Let's just go see what Shannon fault is. It's a dash line. And when we go to that, we see the dash line is a normal fault. Okay? So if you put the other one, if you put that one, that was, okay, what's the next question? We've hit too many things here.
Synclines and anticlines suggest what kinds of strain?
Synclines and anticlines. A syncline would be if the soil is collapsed, that's the trough, that must be a tensional strain. An anticline for a hump, an arch, that must be a compressive strain. Do you see that? Syncline, for it to be a trough there, it must have been a tensional strain. Stress, I'm sorry. Wait. Go back and ask again. Read the question for me again. What kind of strain? Okay, I was giving stresses. Sorry about that. Compressive and other are stresses. These are, what kind of strains are they? Oh, goodness gracious. My mind's going blank on me. That's back in chapter... What was that? That was chapter 19, I believe, building earth surfaces. Okay. Okay. The stresses are your compressive, tensional, and shear. That's what I was giving you. That wasn't what. What we're looking for is strains. The three types of strains are elastic strain, plastic strain, or elastic strain, plastic strain, or fracture strain. And since this is a trough or a arch, this must have been plastic. It didn't break, it just bent, it folded. So you could call that a fold as well, but I think according to the book that would be a plastic strain. The rock units are molded or bent under stress and do not return to their original shape. The elastic, they recover their original shape after the stress is released. The fracture, they break, crack or break, as the name suggests. So these would be plastic strains. That's what they were asking for. Okay, what's the next question?
Faults found in question 7 about suggest what kind of stress?
Okay, stress.
Found in question 7 above suggest what kind of stress?
Okay, and which are you going to focus on, the thrust fault or the normal fault? We put thrust, didn't we? Okay, what kind of stress produces the thrust fault? Okay, if you I think this will do it for you. This picture will. Oops. I don't know why that popped out. Okay. Where it is. There it is. All right. There is the reverse fault. There is the thrust fault. And see what kind of stress those are? The arrows are pointing inward. Those are compressive stresses. Compressive stresses. C-O-M-P-R-E-S-S-I-V-E. How compressive stress, that's what it says under the map, compressive stress could result in a normal or a thrust fault. Goodness, this is hard to do. Okay, if you see the caption there, see how compressive stress, that's the ones that push against each other, where the hanging wall is moved up over on top of the foot wall. Compressive. So that answer is compressive, and I just lost my DVD. I hope it didn't break. Okay. All right, did that answer your question for you? What's the next one?
Go back to the listing of the geologic maps and
Okay.
scroll down until you see Birmingham North.
Okay.
The fourth column where you see QS45 plate 1 and click on it.
Okay. So the GS, I'm back on this. I don't, can you see the top of my screen where the tabs are? There was a QS20 plate 1 that we're looking at. We're now on QS20 plate 2. We're now going back to the GSA, which is a geological blah, blah, blah map. So let's go back there, and we scroll down further until we get to Birmingham. Was it north or south? Okay. Keep on going down until we find, this isn't in alphabetical order or anything. There's Birmingham North. You see it? QS45, and did it say plate 1? Okay, do well. Okay.
Also click on plate 2 in the next column.
Right. Okay.
And on plate 1, move to the part
Right.
of the plate until you see Red Mountain and expand the scale until you can read the contour lines.
Right. So you see where I am here? There's Birmingham North, QS45. You go over a couple columns, you see plate 1, and then right next to that plate 2. So let me do plate 1 first. I probably should close the other two. Let me close the other two because I don't have enough room at the top. Okay. I've got plate 1, so I go back to GSA OGB and do plate 2 now. Open plate 2. Okay. Now we go to plate 1, right? All right. Then I think we go down near the bottom. Red Mountain again, fortunately, is in red again here for us. Where does it say? Oh, no, 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 it's not. There's Red Mountain down there, isn't it? Wait, which one of these is Red Mountain? Okay. While we're here, can you see contour interval 20 feet? Is that one of the questions?
Yes, what is the contour interval of the map?
Can you read that?
20 feet, you said?
Yeah. I'm going to blow it up so you can read it better. Okay. You can't read it now at all. Okay. See the contour interval 20 feet? Is that still not able to read? See it right there, right above Birmingham North. Oh, wait. Jackson's coming in. Sorry about that. I hope I haven't missed anybody else. Okay, welcome back, Jackson. Right in the middle of, let's see. When did you leave? Long?
That question is number 12, just in case.
Okay.
It logged me out at question 5.
Okay, what's that again? Oh, you left at question 9. So you know where we're... I see.
It kicked me out. I didn't even get question 9.
Okay.
Question 9 is plastic.
Okay. And you say we're on 12 now?
You just, yeah, number 12 was what is the contour interval of the map, which was 20 feet.
Okay.
Now we're going to go back to number 11, which is what is the highest elevation you can read on Red Mountain?
Oh, okay. We're going back. Did Jackson need any of the others in between?
Can we get 10?
Yeah, that's what I was going to ask.
Compressive.
Compressive stress. And then we just did 11.
No, we did number 12.
Okay, what's 11? Oh, 11 was the contour interval on this.
12 is 20 feet contour interval.
Right. We're on this new map, Jackson. We're on the one of Birmingham North, but it's so it's a different map. It's plate 45. So you'll have to, if you want to go there and find it, you just go back to the GSA thing and find this one. So, okay. So can you read the 20 feet there, or do I need to expand some? Okay. What's the next question?
What is the highest elevation you can read on Red Mountain?
Okay. Now I'm trying to see. I'm going to blow up a little bit more so I can make sure I can find Red Mountain. I don't know if that's it down here. So far I can't read that. Yes, that's it. That's Red Mountain. Okay. Just a little bit on this map. Okay, there's the very edge. All right. Can we read our numbers yet, or do we need to go up a little bit higher? I think maybe a little bit more. Now, are you sure that one didn't say Birmingham South? No, it said plate 40. Okay. Blow up a little further. Ah, there I see red for Red Mountain. And come down some. Okay. Are we beginning to see our numbers clearer? Let me blow it up one more time. Don't publish this. They'll think I'm a terrorist or something if I'm talking about blowing up Red Mountain. Okay. or a tourist one. I don't know which. Okay. Man, it seemed like before I could read these numbers a lot better than I can now, and it's the same map. Must be getting old or something. Let's blow it up again. Okay, that might do it. Now it's beginning to get a little on the fuzzy side.
I don't think it's because you're old, because I can't read them either.
Okay. All right. Now, I see Altamont Park there. Can you see that? Okay, I see a contour line of 1,000 feet right here. So you see we're well above what we were down in Bessemer. Let's see if I can see any numbers here. Usually they're at the plus signs that you have there. It's where they're located, and I'm not seeing them here. The biggest number I see here is 1,000 right there. And I know it must go a little bit more than that, but I sure can't see any. I see 1,000 there too. There's another water, and usually the high points are near that, but I sure can't make out. Okay. Let's go from this one right here. There's 1,000, and it's a 20-foot interval, so that would be 1020, 1040, and there would be 1060. That's the greatest I can make out on here. Can anyone see anything taller than that?
1060?
Yeah, that's the max I see so far. It's right there under SRM. It's not written there, but I see the 1,000, and then that would be 1,020, 1,040. That would be 1,060. Man, I thought earlier I found an actual number written here, and I just cannot see it now. Seems like somewhere in here it should be, but I can't make it out. So let's go with 1,060, not to waste too much time. So was that the next question?
Okay, number 13 is, what is the lowest contour line you can read near the base of Red Mountain?
Okay. So going down the base, notice how steep that is. Look how those contour lines are so close together. Okay. Let's see what the minimum I can read here. There's one right there. I think I'm going to have to scroll down. That's at 800, but surely we can get something less than 800. There's Cliff Road right there. I've walked along Cliff Road before. It's at the base, but it's pretty far up there. Let's see if we can get anything below that. There's 800 right there. So let's go down from that. That's 800. 20-foot contour, that would be 780, 760, 740, It looks like maybe 720 is about the least I can see. Are y'all okay with that, or can you see anything less than that?
I'm fine with that.
Okay, 720. What was the max? 1060, was that it?
Yes, sir. 1060.
Okay, so the 1060 minus, oops, I just did dividing. 1060 minus, oops, 10, me and my calculator don't get along too well. Minus what did I say, 720 or 740?
Equals 340.
740? Oh, yeah, was it 740? Okay, and that gave
No,
us,
it was 720. You said it was
720.
720.
It equals 340.
oh, 340, equals 340. Got it, that's what I got to. Okay, 340. So the maximum height there would be 340 feet. That's about like we had before, wasn't it? Both the elevation went up, but the base went up too. Okay, what's another question? Next question. Anyone got one?
List at least one syncline found on this map.
Okay. Now I think I'm going to have to go down and scale some. Otherwise I'll be looking forever. Let me draw it in here. Oops, wrong way. It was really nice before when I was right in the corner and the two arrows were close to each other. Come on, where are you? Okay, so we're looking for, you said first a syncline?
Sir.
Okay. My scooting skills are not very good. Okay, so far I haven't seen a syncline yet. Let's keep looking. Okay. Okay, let me keep going down. And over. Haven't seen a syncline yet. I think I see some faults, but no syncline yet. So let's go down on another one. Okay, still looking for my first syncline. This is okay. I hope I haven't gotten the scale so small I can't read it. I would think not. Okay, I think I'm reaching the edge of the map, so let's just go up and see what we get. We're looking for a syncline, right? Now, here's part of the problem. It may be that you folks are in the way. Okay. Ah, I found one. You see it? Can you see where my cursor is?
East Birmingham.
East Birmingham syncline. There's one. Oh, there's another one. There's a Blunt Mountain syncline up here. So you got a choice. Blunt Mountain syncline or East Birmingham syncline. There's at least two of them. All right. What's the next question?
List at least one fault found on this map.
One fault found. Okay, let's see if we can find any fault. We're on a fault finding tour here. Okay, I know there's got to be some here. I see them, but I can't see the names of them. Oh, there we have again. Same one we had last time. You see it? Can you read that any better?
Colbert.
Oh, you found Kohlberg?
Oh no, I'm just saying that's what
Ah, I see a Possum Valley fault. Okay. Does everybody see that one? A Possum Valley fault. Right there. I know there's others because you see them all over the place here. But I can't see a name for them. That one I see a name. A Possum Valley fault. And there it is right there. You probably will recognize it from what we had last time too. Okay. Next.
From plate 2, what kind of fault is it?
Okay, you see the symbol for it? The dashed line with the arrows pointing downward. So go to plate 2 and we see that is, can you read that or do I need to blow it up some? Thrust fault, exactly, just like before. It's a thrust fault. Okay. I bet you if we looked hard enough we'd find the others too. I saw them, but I just didn't see any names for them. Okay. What's next?
From plate 1, list at least one anticline.
One anticline. Okay, let's go back to plate 1. I thought I saw an anticline. Do you see it?
Dickey Springs.
Second, do you see Dickey Springs on there?
It's the same question as number 8.
Yeah, I know, but do you see Dickey Springs on this one? On this map? It may be. I haven't seen it yet. I was just asking, did you see it on this map? If my, okay. But,
The question is the same as what I'm saying.
right. But this is a different map, so I would anticipate, even so a Possum Valley was showed up on both of them, this one is, that's a fault. Do you see where my cursor is down here? Right near the lower right corner. Right next to the blow up things. Anyone see that?
Is that an
Airport anticline, exactly. So evidently the airport was built on an arch, which is sort of interesting, but I guess they could grade the top off and fill in the sides. That's called the airport anticline. Okay, so there's one. There may be others. I wouldn't be at all surprised if there's others. Okay. If you find another one, like if you find Dickey Springs on this map, put it, that'll be fine. I just haven't seen it yet. Okay. What's next?
inclines and anticlines suggest what kind of strain?
Oh, we've had that one before. What was it?
You said plastic.
Plastic, exactly. They're a plastic strain because nothing broke. It just misshaped itself and did not crack or fault. So therefore, that would have been a plastic strain. Okay.
Number 20 is the fault found in question 17 above suggests what kind of stress, and we know that that is compressive stress.
Yes, because the thrust faults or a reverse faults are both compressive stresses. The normal faults are tensional stresses. And
What was number 15?
what was the question?
List at least one syncline found on this map.
East Birmingham.
East Birmingham.
Either East Birmingham syncline or Blunt Mountain syncline. There were two of them that were right near each other. Those were trough type areas. It finds it interesting they have named that after a mountain, but that's a trough that's at the base of Blunt Mountain, is what my assumption is. All right. Now, just to give you an idea, not that you need to know this, but if you go back down there to Red Mountain, that was in the lower left corner, you see that neighborhood right there called Forest Park? We are somewhere, I live somewhere right down, I can't make it out here, but I know where Avondale, that's fairly close to us. I think this is a street right here. I think this is Claremont. Right down here where it makes that big bend in the road and goes back up, we live right there in that block right there. I believe it is. Yeah, so that's real close to where I live. So anyway, not that you need to know that. The other one, the Bessemer, was right close to where we used to meet for this class, and that was on the Bessemer State Technical College campus. It's the Bessemer campus of Lawson State now. All right, now I didn't go through with you on the Devil's Tower, but just like we found this on a geologic map here, you might have to go to Wyoming and find a geologic map, or I don't know, all my classes before have been able to find something there, so you can work together as a group, individually, whatever, and answer those 5 questions based on Devil's Tower Monument or something like that, whatever that was on the last page, I think it was, of the PDF file. That one, no, okay, you did 5 questions on the first part of the PDF file. Okay, let's go back to it. I'll show you. That's this one. Okay, well, I don't see anything there. What happened to it? Okay, yeah, there it is. That was on this page, Devil's Tower National Monument. Okay, you'll just have to find. I don't think the last time I checked, I couldn't find that web address. I think University of Texas must have gotten out of that part of it. So you'll just have to go out there, Google any other search engine, and look for Devil's Tower National Monument. Make sure it's in Wyoming. And if you need any more, be sure it's either a relief map or a topographic map. I like the term topographic better, but it may be listed under relief. And then once you find that, just like we found that one, the GSA map that we were just looking at for Birmingham and Bessemer, find the map, whatever relief map you find, and then read the contour lines, the contour interval, and calculate the elevation and read the elevation, calculate the approximate height, and then see if you can just either from the evidence there tell what the top of it was like, or you might find an associated document like we had there that maybe told you what the top was like. And then you come up with the idea whether it's too steep to hike to the top. I'm sure you can mountain climb to the top, but you figure out whether it's too steep to hike. I'll guarantee you it's going to be a lot steeper than Red Mountain was. Okay, I think those contour lines are going to be really close together. Okay, so we had 5 questions on previous to this. Okay, let's just go back and review that. Remember, the first 5 questions were basically on your reading. Well, the first 4 were on your reading. The reading is located, and unfortunately that one came out really fuzzy. The reading is on the first page here, the one that says topographic maps. That page number here is 345. Then the most answers are on 346. Those 9 right up there, you'll find most of the rest of the answers there. So read 345 and 346, and then the 2 questions on 347, and the top 2 questions on 348. And then once the end of the lab is over, you answer question 5. Okay? Then the next 5 questions come off whatever you can find on Devil's Tower National Monument. Remember, we had a picture of it in the book, so you can look at that picture in the book as well. That was on page 349. And then the rest of the questions came off the PowerPoint that I can't see on my screen anymore. Where is that it? Yeah, there it is. You probably can't see it now. But that's what, was it Angelita, were you the one reading those for me? Okay. You had, what was it? Something like 13 questions there. 9, 10 on the first page, and another 10 on the second page. So you have a total of 20 questions here, 10 questions on the rest of it. So you have a total of 30 possible answers, and I'll grade it on that. So they'll count a little less than a point each. Okay, so that way you might miss half of a question and still be able to get a 25. So any questions on this? Okay, do you want me to stay with you until a little bit more, or are you happy to go on and start search for Devil's Tower on your own?
Good to go.
Good to go? All right then. Now also the other thing is I'll put the chapter 20 test. I don't think I've posted that yet, so I'm going to try to post it in 2 places. One place will be under week, since we're in week 6 now, I'll put week 6 assessment, but I'll change the title to be chapter 20 test, and in parentheses put test, what is that, up to test 7. Okay, I'll also put it on the Blackboard message, whatever you call that, Blackboard messages. So I'll post it in 2 places. Week 6, it'll say chapter 20 test or test 7, something like that, and then I'll also post it on Blackboard messages. Okay, any questions? Okay, I'll take it. I may have lost most of the people now. Okay, unless there are questions, I'll stop the sharing now. Okay, any last questions? Okay, I'm going to stop sharing, and then I will go on and end the session. Anything else? Anybody? I see a lot of chats have been going. Are any of those directed toward me, or are you just talking among yourselves?
Mr. Fowler?
Yes. Okay. Yes. Was Matthew, you say something?
Yeah, on the like the back of the PDF lab, not the first part of the lab.
Yeah.
The I looked up the map and like to see how we were looking at it, but I'm not finding some of this stuff. I'm not really sure what to do.
Okay. Now, okay. You had 5 questions at the beginning, which are based on the first 2 pages, right?
Yeah, I understand. I'm talking about the very, very last question, that the inquiry thing.
Oh, the ones on Devil Tower National Monument. Is that what you're talking about?
Yes, sir.
Okay. What did you try? Okay. Okay, here's what I'm going to suggest. Let me see if I can go to, why did that do that? Okay. All right. I'm going to go to my search engine. You see Google there? Okay, you might not be able to see it. Okay, let me see if I can get back on here so you can see what I'm doing. Google Meet, or Zoom meeting, and share screen. See, I've just got so many things open. New tab, that's it. Okay. Okay, you see where I am now? Okay. And I don't know which you want to search from, here or there. Let's do it here. Okay. Let's do devils. If I can remember how to spell it. Tower, was that right? Ah, Devil's Tower National Monument, right there. You see it on my screen? Okay, I'm going to click on that. Okay, I'm going to have to move y'all out of the way, I think. Matthew, you're in the way again. So let's see if I can move you up here. And let's see. Okay, let me, whoops. I'm trying to move this taskbar out of the way so I can read better. Okay. There's images. Let's see. Climbing, class encounters, bear, top. There may be some answers there.
So I was able to click on one of the, I think it's probably one of the first ones. It took me to a map kind of similar to the one you had, but it didn't have everything.
Okay. You've been here before then. That's why I asked you, where had you gone? Right here.
Maybe it was the,
Okay, you're fading out.
I pressed on, try pressing on the first, like that first thing that popped up at the top.
Devil's Tower National Monument, U.S. Park Service. Okay. Wait, here's maps. There's maps. I'm going to click on maps. Okay. Let's see. Gerald, you're in the way again. Okay, let me get over here. Okay. I don't see anything there. I'm going to click on maps again here. Okay. Well, it keeps going to alerts in effect. So I'm going to move this out of the way. Okay. Let's see if I can get to maps. I keep trying to get there and it's not. Ah, there's maps. Okay, let's see if we can find. That kind of looks like a contour map, but I'm not sure that it is. It looks like that's more of a street map. Let's try a map box and see what happens. That may be just who published it. No, I don't think that's what I want. Let me go back. Yuck. I don't want that. Okay, that's what I want. Okay, I don't want map box. Okay. This looks like a contour map, doesn't it? You see what I'm doing? Okay. Now, I think you can read right here. Okay. There looks like this elevation to me. Doesn't it to you? Okay. Now, that was the first question. The next question said, what was the contour interval, right? So I want to scroll down. How do I do that? Okay. Oh, here we go. The minus is to scroll down. See if we can get to the contour interval here somewhere. I don't see a contour interval. Okay, so let's go back up here. We'll figure it out by, okay, I think that's the max. Okay, here's 1400 meters here. Okay, this is in meters. That's in feet. That's a shame. Okay, why would they do that? Okay, but the contour intervals are, here's 1400 meters here, and you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 in between 14 and 1500, so it looks like each one of those must be that's the difference of yeah, that's exact. No, 10 meters, 10 meters, because you see this would be 1400 meters. It'd be 14, 10, 20, 30, 40, 50, 60, 70, 80, 90, 1500. So it looks like a 10 meter. the elevations in feet, but the contour intervals in meters. That's bizarre. Okay, but it's true. Okay. Now, what's the next one? What's the approximate height? Right. Now that you might have to do some more figuring on. And it says approximate, so you can find this would be 15, 10, 20, 30, 40, 50. It looks like about 1550 meters is to the outer circle here. And then let's see what it is from the base. Let's see if we can figure out what the base is. Let's go down here. There's 14, and you go down 10 meters at a time. That's 1390, 1380, 1370, 1316, 60, 1350, 1340. That may be it. So 1340 to, what do I say, 15, was it 1560? 1510, 20, 30, 40, 1550, and 1340. So do a subtraction there and you get how many meters to the top. Right? Okay. And what was the next one?
The next one says, what is the top of the Devil's Tower look like, or what is it like?
What is it like? Well, if you see it was going up all that thing there and you don't get to the next one, so you have a feeling it's fairly flat, but I would think maybe slightly domed. Okay? Now, that would be a first guess. And what's the next one?
The next one, the number 5 says, is the Devil's Tower too steep to hike to the top?
Okay, what do you think?
I don't know anything about hiking, but probably.
Now, look how close those contour lines are. Okay, so let's back out of this I think maybe that is going to give it to us. And see what else. Wow, I didn't know it was that close to Black Hills. Okay. Somewhere else where we were before we were here at maps. Ah, this one. Okay. Oh boy, look at that. A possible laccolith. Remember that? That's a place where a very narrow dike came up and magma went underneath, and then everything else went away. Now take a look at that. Think you want to hike up there?
Not really.
Me either. Okay. Um, Here is in feet what we figured in meters. It's that far above Belle Fourche River, but standing 867 feet from summit to base. So that's the height right there. The elevation right here. We didn't even need to go to a map, but I'm glad we did. Okay. Do they say anything about what the top is like? Okay. These are different pictures of it. You decide whether you want to hike it. Okay, that's interesting. It's First National Monument. Okay. So you can look around and find more about it if you're interested. But I think you got pretty much what you needed, didn't you?
Yeah, I think I got everything. Thank you so much.
All right, glad to. Any other?
It is too steep to hike.
Okay, that'll be up to you. What do you think? There it is, several shots of it. You think you want to hike that? And you see it's in reference to a house there. I don't think I do either. Now this guy down here said recommended hiking climbing shoes backpack. Okay, I think he's talking about climbing it, not talking about hiking it. To me, a hike is a little more gradual than that. But I'll let you answer that for yourself. Okay. It looks a bit daunting to me. I think a mountain climber could probably climb it. But there's interesting. I hadn't seen this word anywhere but our text until now, a laccolith. You can read that, and I think it was the chapter 19, right at the end of the chapter. So there are several things. That is its height in feet. We calculated it in meters, so we should have had there. There's the elevation compared to the height. And they said ascent here, which I have a feeling means a rock climbing thing rather than a hike. Okay. In my mind, that's mountain climbing. That's not a hike. Okay. Any other questions? All right to shut that one down?
Yes, sir. I think we're all good.
Okay. So that means stop sharing. I'm sick and tired of sharing. Okay, I'm going to stop the sharing then unless there's any more questions. And, ooh, we only got 4 of you left. So, all right, to end the recording. I mean, not the I will end the recording, but I'm going to end the meeting. We're 7 minutes short, so I'm cheating you out of 7 minutes of your tuition dollars, but a lot of other people left cheaper than that. Okay. So take care. We'll see you on Thursday. Okay. And we'll wrap up chapter 19 or 23 or come pretty close to it anyway. All right. Take care.